What if the universe isn't as simple as it looks? What if every choice you make, every star you see, and even your very existence is tangled in paradoxes that science still can't fully solve? From the mysteries of quantum physics to the riddles of free will and time, these paradoxes don't just puzzle us, they change the way we see reality itself. In this video, we're going to dive into the most mind-bending ideas that will leave you questioning everything you thought you knew. So stay with me, and before we begin, make sure to like this video, subscribe, and drop your thoughts in the comments, because your perspective might uncover another piece of the puzzle. The quantum observer effect. Does reality exist when no one is looking? Imagine you're standing in a dimly lit room staring at a closed door. You know what's behind it: a chair, a lamp, maybe a desk. But here's the question. When you turn away, does that room still exist exactly as you remember it? Or does reality itself fade into uncertainty the moment you stop looking? It sounds absurd, almost like a riddle from a dream. But this is the very heart of the quantum observer effect, a mystery that has haunted scientists and philosophers for over a century. It suggests that reality may not be fixed and solid the way we like to believe. Instead, it may be fluid, shifting, and even dependent on whether someone or something is watching. To truly understand this paradox, we need to travel into the strange world of quantum physics, where the tiniest building blocks of matter refuse to behave in ways we expect. In our everyday world, objects are predictable. A ball rolls across the floor, a chair stays where you leave it, and a lamp does not suddenly turn into a cloud. But in the quantum world, the world of electrons, photons, and particles smaller than atoms, things don't follow the same rules. You might think of an electron as a tiny marble moving along a clear path. But when scientists performed the famous double-slit experiment, they found something shocking. When electrons were fired at a barrier with two slits, they didn't pass through one slit or the other. Instead, they created an interference pattern on the other side, as though each electron passed through both slits at the same time, behaving like a wave spread out across space. This was already bizarre enough, but the truly mind-bending part is when scientists placed a measuring device at the slits to see which path the electron actually took. Suddenly, the wave-like pattern disappeared. The electron chose one slit or the other, behaving like a solid particle. It was as if the electron somehow knew it was being observed and decided to act differently. In other words, the mere act of observation forced the electron to make a choice. Without observation, it remained in a ghostly cloud of possibilities. With observation, it snapped into one definite outcome. This is the observer effect, the strange fact that measuring or observing something at the quantum level changes its behavior. But what does this mean for reality itself? If the smallest pieces of matter only decide what state they're in when they're observed, then what exists before anyone looks? Is reality itself just a blur of endless possibilities, waiting for consciousness to shine a spotlight on it and make it real? The implications are staggering. It suggests that the universe, at its most fundamental level, does not run on rigid laws alone. Instead, it flows like a dance between probability and existence, becoming solid only when something or someone is there to witness it. Some physicists argue that observation doesn't have to mean human consciousness. They say that even a photon of light bouncing off a particle counts as observation, collapsing the uncertainty into a definite outcome. But this explanation doesn't completely remove the paradox. Why does the act of measurement matter at all? Why should the universe care whether it is being watched or not? Why should the behavior of matter shift based on attention? And if that's true, what about the universe beyond our perception? Think about the cosmos before life existed. For billions of years, stars were burning, galaxies forming, and planets spinning. But if there were no observers, no conscious beings, did the universe exist in a definite form? Or was it a vast haze of probabilities, waiting for something to look at it and bring it into focus? And if humanity to disappear tomorrow, would the universe continue on its own? Or would it simply dissolve into nothingness until another form of awareness emerged to notice it? Even Albert Einstein struggled with this. He famously asked, "Does the moon exist only when I look at it?" To him, reality had to exist independently of observation. After all, how could the universe depend on whether humans happen to be watching? But quantum mechanics continues to defy that simple comfort. Over and over again, experiments show the same eerie truth. Reality, on the smallest scale, does not settle into place until it is measured. So what does that make you? Are you simply a spectator of reality, passively observing a world that unfolds on its own? Or are you, in some strange and fundamental way, helping to create it? Maybe reality isn't like a fixed book already written, but more like a script that only comes alive when the spotlight of awareness falls upon it. Perhaps every moment you see, every object you touch, every sound you hear is just one version of what could have been, chosen in the instant your consciousness became aware of it. If that's true, then reality itself is not just out there, independent and untouched. It is deeply connected with you. You may not just be looking at the universe. You may be helping to bring it into existence. Schrödinger's cat. A cat that is both dead and alive until observed. It sounds like a cruel joke or an impossible riddle, but this is the strange world of quantum mechanics. Imagine standing in front of a closed box. Inside, you are told, there is a cat. But here's the twist. Until you open the box, the cat isn't simply alive or dead. According to the strange rules of quantum physics, it exists in both states at once, alive and dead, caught in a limbo of uncertainty. Only when you open the box does the universe choose, and reality snaps into clarity. The cat becomes either alive or dead, and the uncertainty disappears. This thought experiment, known as Schrödinger's cat, is one of the most famous and unsettling illustrations of the paradoxes within quantum mechanics. It wasn't originally designed to explain reality, but to expose how absurd quantum laws sound when applied to everyday life. Erwin Schrödinger, the physicist behind the idea, wanted to show how strange it was to suggest that particles can exist in two states at once. Yet, instead of dismissing the problem, his cat forced the world to confront an uncomfortable truth. The universe may not be as definite as we believe. Here's how the setup works. Picture a sealed box. Inside, there's a cat, a vial of poison, and a device triggered by the decay of a single radioactive atom. This atom is so tiny that its behavior follows quantum rules. It can decay or not decay, and until it is observed, it exists in both possibilities simultaneously. If the atom decays, the poison is released and the cat dies. If the atom doesn't decay, the cat lives. But here's the disturbing part. Quantum mechanics says that until the box is opened and the atom is observed, the atom exists in a state of superposition. It has both decayed and not decayed. And because the cat's fate depends on the atom, the cat too exists in superposition. It is alive and dead at the same time. Think about the horror of that idea. The cat's very existence, its fate, isn't decided until you look. Before you open the box, there is no single outcome. There is only probability, a blurred cloud of possibilities, both life and death, existing simultaneously. In the everyday world, this sounds impossible. How can a cat be both alive and dead? But in the microscopic world of particles, this is not just theory, it's fact. Experiments have shown that electrons, photons, and even molecules can remain in multiple states until they are measured. Superposition is not just philosophy, it's reality. So, what does this mean for us? Does superposition apply to the macroscopic world, the world of cats, people, and planets? Or is it limited to the tiny realm of particles? Schrödinger himself didn't believe the cat was literally alive and dead. His experiment was meant to highlight the strange problem of interpreting quantum mechanics. But as science advances, the line between the quantum and the everyday begins to blur. Molecules far larger than single particles have been placed into superposition, existing in multiple states at once. If superposition scales up, where does it stop? Could you, in some sense, exist in many states at once until observed? Physicists have proposed different interpretations to deal with this paradox. The Copenhagen interpretation suggests that observation collapses superposition into one outcome. The cat becomes alive or dead only when measured. Reality is not definite until it is witnessed. On the other hand, the many worlds interpretation offers something even stranger. It says that when you open the box, the universe doesn't collapse into one version, it splits. In one universe, you find the cat alive. In another, you find it dead. Both outcomes exist, but in separate parallel realities, and you only experience one of t. Now imagine what that means for you. If the many worlds interpretation is true, then every decision, every observation, every moment of your life may be splitting reality into countless branches. In one universe, you turn left. In another, you turn right. In one, you answer a call. In another, you don't. There could be endless versions of you, living out endless versions of reality, each one diverging from a simple moment of choice or observation. Schrödinger's cat forces us to confront a question that refuses to die. Does reality exist in a definite form before we observe it? Or is everything around us just a blur of probabilities, waiting to be resolved by our attention? Are we simply observers of a pre-existing universe? Or are we creators, collapsing possibility into reality each time we look? Perhaps the cat in the box is more than just a thought experiment. Perhaps it's a mirror of our own existence. Maybe, until we open the box of life itself, we too are suspended between infinite possibilities, waiting for observation to shape who we truly are. Wave-particle duality. Light and matter act like both particles and waves. At first glance, that sounds impossible. How can something be both a solid object and a ripple spreading through space? Yet this is one of the strangest and most unsettling discoveries in physics. Imagine flicking on a light switch. Instantly, photons, tiny particles of light, scatter across the room, bouncing off walls, furniture, and your skin. In everyday life, it feels natural to think of them as little particles, like bullets shooting through space. But when scientists studied them more closely, they discovered something shocking. Sometimes, light behaves not like a particle at all, but like a wave. To understand this paradox, we need to revisit one of the most famous experiments in science, the double-slit experiment. Take a beam of light and shine it at a barrier with two narrow slits. If light were just a stream of particles, we would expect it to pass through one slit or the other, creating two neat clusters on the screen behind the barrier. But that's not what happens. Instead, the light spreads out, bends, and interferes with itself, creating a series of bright and dark bands. This is the signature of a wave, not a particle. Waves can pass through both slits at once, overlapping and interfering, just like ripples in a pond. Light, it seemed, wasn't a particle at all. It was a wave. But here's where the paradox deepens. When scientists placed a detector at the slits to measure which path the photons took, the interference pattern vanished. Suddenly, light behaved like particles again, forming two distinct bands instead of a spread-out wave. Somehow, the act of observation determined how light behaved. When left alone, it acted like a wave. When measured, it acted like particles. This phenomenon is known as wave-particle duality. It tells us that light, and even matter itself, does not have a fixed identity. It is not simply a particle, nor simply a wave. It can behave as either, depending on how it is observed. This discovery didn't just apply to light. Electrons, the tiny particles that make up atoms, also display this dual behavior. Fire electrons one at a time at a double slit, and they too create an interference pattern, as if each electron passes through both slits simultaneously. Yet, if you measure which slit they go through, they act like solid particles. Think about what this means. The fundamental building blocks of the universe don't behave in a fixed, predictable way. They exist in a strange in-between state, sometimes spreading like waves, sometimes hitting like particles, their true nature hidden until observed. And this doesn't just stop with electrons. Even larger systems, atoms, and even molecules have been shown to exhibit wave-like behavior under the right conditions. It's as if everything in existence, even the matter that makes up your body, contains this strange duality. So what's really happening? Some interpretations of quantum mechanics suggest that before being measured, particles don't exist in a definite state. Instead, they exist in a superposition, a cloud of probabilities, both wave and particle at the same time. The act of measurement collapses this uncertainty into one outcome. In other words, reality isn't fixed until you look at it. Another explanation is the many worlds interpretation, which offers an even more mind-bending possibility. It suggests that when a particle decides whether to behave like a wave or a particle, both outcomes actually occur, but in separate universes. When you measure a photon, the universe splits. In one version, you observe it as a particle. In another, you observe it as a wave. Every possibility exists, but in different branches of reality. Wave-particle duality challenges our most basic assumptions about reality. We like to think the world around us is solid, definite, and predictable, but at its core, existence is not fixed. It shifts, bends, and transforms, depending on whether it is being watched. The universe, it seems, is not simply out there, existing independently of us. It is, in some profound way, entangled with our observation. And here's the most unsettling question of all. If matter itself doesn't decide what it is until it is observed, then what does that say about us? Are we just passive witnesses of a strange reality, or are we active participants shaping it by the simple act of looking? If light can be both wave and particle, what else in the universe is waiting to take shape only when you pay attention? Wave-particle duality is more than a physics puzzle. It's a crack in the foundation of reality, whispering that the world may be far stranger and far less certain than we ever imagined. The black hole information paradox. Does information get lost in black holes or not? Imagine falling toward one of the most terrifying objects in the universe, a black hole. At first, space still looks familiar. Behind you, stars sparkle and galaxies stretch out like a cosmic painting. But as you approach the black hole's event horizon, the invisible boundary beyond which nothing can escape, you enter a place where the known laws of physics begin to collapse. Once you cross that threshold, everything changes. Space bends, time stretches, and in an instant you vanish. Not just your body, not just your atoms, but perhaps even the information that defines you, the very blueprint of your existence, may be erased forever. This is the black hole information paradox, one of the greatest puzzles in modern science. It raises a seemingly simple but devastating question. What happens to information that falls into a black hole? At first, you might think it's obvious. If something is destroyed, burned, crushed, or swallowed by a black hole, then surely the information about what it once was disappears with it. But physics insists that this cannot be true. Here's why. The foundation of physics is built on the principle that information is never destroyed. It can be scrambled, transformed, or hidden, but not erased. If you burn a book, for example, the words disappear, but the information isn't gone. It's scattered in the smoke, heat, and ashes. In theory, if you had perfect knowledge, you could trace every particle and reconstruct the book. This principle, that information is preserved, is at the heart of physics. Without it, cause and effect break down, and the universe itself becomes unpredictable. But black holes appear to defy this principle. According to Einstein's theory of general relativity, black holes are regions where gravity is so intense that not even light can escape. Anything that crosses the event horizon is trapped forever, pulled toward the singularity at the center, a point of infinite density where our current understanding of physics completely fails. Once something falls in, it seems all distinguishing information about it, whether it was a star, a planet, a spaceship, or a single particle, vanishes. From the outside, black holes look identical no matter what they swallow. They are defined only by three simple properties: mass, charge, and spin. Everything else is erased. This creates a devastating contradiction. If black holes truly destroy information, then one of the most fundamental principles of physics is broken. The universe would no longer be deterministic. The past could not always be reconstructed from the present. In other words, physics itself would collapse. And then Stephen Hawking made things worse. In 1974, he showed that black holes are not completely black. Thanks to quantum effects near the event horizon, black holes emit faint radiation, now called Hawking radiation. This radiation slowly drains the black hole of its energy, causing it to shrink and, over unimaginable timescales, evaporate entirely. But here's the catch. Hawking radiation carries no information. It is random, like static noise. If the black hole eventually disappears, taking with it all the information it had swallowed, then that information is lost forever. The paradox was now unavoidable. Either black holes erase information, breaking quantum mechanics, or quantum mechanics is correct, and our understanding of black holes is fundamentally flawed. So, where does the information go? Scientists have proposed several possibilities. One idea is that the information remains hidden inside the black hole, beyond the event horizon. But this only delays the problem. Once the black hole evaporates, the information would still vanish. Another possibility is that the information leaks out, somehow encoded in subtle patterns in Hawking radiation. If true, this would mean that black holes do not destroy information, but instead scramble it into a form so complex we cannot yet decode it. However, no one has proven this. Then comes the holographic principle, one of the most radical ideas in physics. It suggests that all the information swallowed by a black hole isn't lost inside, but instead imprinted on its surface, the event horizon itself, like a cosmic hologram. From this perspective, the three-dimensional contents of the black hole are just a projection of data stored on a two-dimensional surface. If true, this wouldn't just apply to black holes, but to the entire universe itself. Reality might be two-dimensional at its core, with the third dimension emerging as an illusion. Still, the paradox refuses to die. Some physicists argue that information is preserved, but in ways so strange they defy intuition. Others suggest that black holes might connect to other universes through wormholes, spitting information elsewhere. Still others propose that perhaps our entire understanding of space, time, and gravity is incomplete, and the paradox is a clue pointing toward a deeper, unified theory. The implications of this paradox are staggering. If information truly is lost in black holes, then the universe itself may be capable of forgetting. History could dissolve, cause and effect could unravel, and reality would no longer be governed by order, but by chaos. On the other hand, if information is somehow preserved, then black holes are not seismic erasers but cosmic safes, storing the deepest secrets of the universe in ways we have yet to understand. The black hole information paradox forces us to confront a terrifying truth. We do not yet understand the most extreme objects in the cosmos, and perhaps we do not yet understand reality itself. Are black holes the ultimate destroyers, erasing the record of existence? Or are they the keepers of a hidden code, holding the answers to the deepest mysteries of physics? Until we solve this paradox, every black hole remains not just an abyss in space, but an abyss in our understanding of truth itself, the Fermi Paradox. If the universe is full of planets, where is everyone? On a clear night, you stand under the stars and feel the immensity of the cosmos pressing down on you. The Milky Way alone holds over 400 billion stars, and beyond it lie trillions of galaxies. Logic suggests that among these countless suns and planets, intelligent life should not just exist, it should thrive. With so many opportunities, there should be civilizations far older and more advanced than ours. Yet, when we listen to the silence of space, we hear nothing. No signals, no visitors, no undeniable signs of alien life. This contradiction between probability and evidence is known as the Fermi Paradox. The paradox takes its name from physicist Enrico Fermi, who famously asked, "Where is everybody?" If life is common in the universe, then intelligent life should have had plenty of time to spread across galaxies. Even at modest speeds, a spacefaring civilization could colonize the Milky Way within a few million years, a blink of an eye compared to the galaxy's age of more than 13 billion years. If even one civilization had achieved this long ago, their presence should be obvious. And yet, our skies remain empty. So where are they? One possibility is that intelligent life is extraordinarily rare. Perhaps the conditions for life are so specific and so delicate that Earth is an exception against impossible odds. Maybe something about our planet, its distance from the sun, its stable climate, its magnetic field, created the perfect recipe for complex organisms, and this recipe is almost never repeated. In this view, we may truly be alone, a solitary voice in a silent universe. But another possibility is even more disturbing. Maybe life is not rare, but short-lived. This is the idea of the Great Filter. Somewhere along the journey from simple microbes to advanced civilizations, there may be a nearly impossible barrier that most species cannot cross. Maybe life often begins, but almost always fails to evolve into intelligence. Or worse, maybe intelligence is common, but it inevitably destroys itself. Civilizations might invent technologies faster than they can manage their consequences. Nuclear weapons, artificial intelligence, environmental collapse, or other self-inflicted catastrophes might wipe them out before they spread across the stars. If this is true, then perhaps we are not early. We are just next. Another explanation is that we are simply not listening correctly. Maybe alien civilizations are communicating, but not in ways we recognize. Our radio telescopes scan for familiar signals, but advanced species might use technologies far beyond our imagination. Laser pulses, quantum communication, or methods we haven't yet discovered. It would be like ancient humans listening for drums in the forest, while others are speaking across oceans with satellites. The silence we hear may not be true silence at all. There are also darker ideas. What if the universe is not silent, but deliberately quiet? One theory, known as the dark forest hypothesis, suggests that civilizations avoid broadcasting their existence out of fear. Imagine a forest at night. Every creature moves carefully, silently, aware that predators may be lurking. Perhaps the cosmos is like this, a dark forest filled with hunters. Any civilization that announces itself risks being destroyed by something far more powerful. If that's the case, then the silence of the stars isn't a mystery, it's a warning. Other possibilities are stranger still. The zoo hypothesis suggests that advanced civilizations know we exist, but deliberately avoid contact, watching us like animals in a protected reserve, waiting until we are ready. Or maybe we are simply too primitive to notice the evidence already around us. Perhaps the signs of alien life are hidden in plain sight, encoded in phenomena we dismiss as natural or misunderstood as noise. And then there is the possibility that we are the first. Perhaps life is only just beginning to awaken across the universe, and humanity is one of its earliest experiments. If this is true, the silence is not a sign of loneliness, but an invitation. We may be among the first intelligent beings to emerge, and the responsibility of spreading life and knowledge across the cosmos rests on our shoulders. The Fermi Paradox forces us to confront two terrifying possibilities. Either we are truly alone in the universe, making life the rarest miracle of all, or we are not alone, and something powerful, mysterious, and possibly dangerous is preventing us from hearing the others. Both answers are deeply unsettling. If we are alone, then the weight of existence falls entirely on humanity. We are the sole voice of consciousness in an otherwise indifferent cosmos. But if we are not alone, then silence may mean danger, or worse, doom. So the question lingers, are we early, are we rare, or are we doomed? The night sky refuses to answer. It only stares back, vast, silent, and infinite, leaving us to wonder what waits out there in the dark, and why it has not yet found us. The Grandfather Paradox. Could you travel back in time and erase your own existence? Imagine stepping into a time machine, its gears whirring as it powers up. You set the date, not for the future, but for the distant past, long before you were ever born. The machine rattles, space bends, and suddenly you find yourself in another era. There, walking through the streets of a world untouched by your presence, you see a man, your grandfather in his youth. He does not know you. He has no idea what you are about to do. And in a single, fateful moment, you stop him before he ever meets your grandmother. What happens next? By preventing their meeting, you prevent your parents from ever being born. And if your parents never exist, then you never exist. And if you never exist, then how did you travel back in time in the first place? This is the Grandfather Paradox, a thought experiment that reveals the logical contradictions at the heart of time travel. At its core, the paradox asks, what happens when cause and effect begin to loop back on themselves? Normally, time feels like a straight line. The past leads to the present, and the present shapes the future. But in the Grandfather Paradox, the line folds in on itself. If you erase your past, you erase your ability to travel back, which means your past is never erased, which means it is erased again. Reality gets trapped in an endless cycle of contradictions, unable to resolve itself. So how do scientists and philosophers attempt to solve this puzzle? One idea is that the universe protects itself through something called the Novikov self-consistency principle. According to this view, time travel to the past might be possible, but you cannot change history in a way that creates a paradox. The timeline defends itself. If you tried to eliminate your grandfather, something would always intervene. The gun jams, you trip, or some a lie accident prevents you from completing the act. You can interact with the past, but never in a way that changes the outcome. The story remains consistent no matter what. But another possibility is far stranger, the many worlds interpretation. In this scenario, the moment you alter the past, you don't erase your own existence. You simply create a new timeline. If you prevent your grandfather from meeting your grandmother, you generate a branch of reality where you were never born. But the original timeline, the one where you did exist, continues to move forward unchanged. In this view, time is not a single river flowing in one direction. It is an endlessly branching tree, with each choice, each alteration, each paradox creating new universes. You don't eliminate yourself. You just step sideways into a version of reality where you never existed. But this solution raises its own disturbing questions. If there are infinite branching timelines, then there may also be infinite versions of you, one who existed, one who didn't, one who made a different choice, one who never even touched the time machine at all. Which one is the real you, or are all of them equally real? The grandfather paradox also forces us to rethink the very nature of time. Is it truly a fixed sequence of events, or is it something fluid and malleable? If time can be altered, then the past, present, and future are not as rigid as we assume. And if time constantly branches into new realities, then perhaps no moment is truly permanent. Everything exists as one possibility among countless others. Even if time travel were possible, could you ever know if you had changed the past? If reality itself shifted to accommodate your actions, your memories might be rewritten to fit the new version of events. You might never realize anything had been altered at all. In fact, you could already be living in a universe shaped by some other traveler's interference, your entire history rewritten without your knowledge. The grandfather paradox is not just a thought experiment about killing an ancestor. It is a challenge to the very idea of reality. It asks whether cause and effect can truly be trusted, whether time is a solid path or an unstable web of possibilities, and whether identity itself survives in a universe where history can be endlessly rewritten. So the question remains, if you had the chance to change the past, would you dare? And even if you did, would you ever know what you had really done, or would the universe quietly rearrange itself around you, leaving you forever uncertain of what was real in the first place? The Bootstrap Paradox: can something exist without ever being created? Imagine this. You are a scientist working late in your lab, when suddenly a stranger appears and hands you a worn-out book filled with detailed instructions for building a time machine. You study it, follow the designs, and after years of work, you succeed. You travel back in time, eager to thank the person who gave you the knowledge. But then you realize the truth. The person who handed you the book was you. You gave yourself the very information that allowed you to build the machine. Here lies the Bootstrap Paradox, a mind-bending puzzle about time, causality, and existence. It describes a scenario where something, a piece of information, an object, or even a person, exists in a time loop with no clear point of origin. The information is passed from the future to the past, then back to the future, over and over, without ever being created in the first place. It is self-generated, a loop without beginning or end. The paradox takes its name from the phrase, pulling yourself up by your own bootstraps, an old saying that implies doing the impossible, lifting yourself into the air without anything to stand on. The Bootstrap Paradox does exactly that. It creates existence without a source, an effect without a cause. To see how strange this gets, let's consider another example. Imagine a composer who receives a piece of sheet music from a mysterious visitor. He publishes it, and it becomes famous. Years later, he grows old and decides to travel back in time, carrying the same sheet music. He hands it to his younger self, ensuring that he will one day publish it. But here's the problem. Who originally wrote the music? The younger version got it from the older version, but the older version only had it because the younger one published it. The loop closes on itself. The music has no true creator. It exists, but its origin is missing. This challenges one of the deepest assumptions we hold, that everything must have a cause. Our entire understanding of reality rests on the chain of cause and effect. One event leads to another, and the past determines the future. But the Bootstrap Paradox breaks this chain. It suggests that some things might exist without a cause at all, sustained purely by the loop of time. Physicists and philosophers debate whether such loops are possible. Some argue that they are ruled out by the laws of logic, that information or objects cannot exist without origin. Others point to the mathematics of general relativity, which does not strictly forbid closed time loops. In fact, certain solutions to Einstein's equations allow for paths through space-time that circle back on themselves. In such universes, bootstrap paradoxes might not just be possible, they might be inevitable. But the paradox raises deeper questions. If information can exist without origin, what does that mean for knowledge itself? Could humanity one day solve problems not by discovering answers, but by receiving them from the future? If so, are those answers truly discoveries, or just echoes trapped in a time loop? Could some of the greatest works of art, science, or literature in our world already be the result of such loops, handed down by versions of ourselves from other points in time? And then there is the unsettling thought of identity. Could a person themselves be caught in a bootstrap loop? Imagine meeting someone who turns out to be your older self, who guides you through life, only for you to become that person years later. In this loop, who are you really? A product of your own choices, or a shadow of a path already locked into place? The Bootstrap Paradox bends not only time, but also meaning. It suggests that perhaps not everything in existence needs a beginning. Perhaps the universe itself could be a kind of bootstrap loop, a reality that creates itself, with no outside cause. After all, if an object or idea can exist in a loop without origin, why not the cosmos itself? The paradox forces us to question whether cause and effect are as absolute as we believe. It whispers that maybe, in some corners of reality, existence is not born but sustained, endlessly circling itself like a serpent swallowing its own tail. So the next time you encounter an idea, a story, or a discovery that feels timeless, ask yourself this: did it have an origin, or could it be part of a loop? Knowledge passed back through time, with no beginning and no end? If so, the very idea of creation might be an illusion, and the Bootstrap Paradox might not just be theory, but the hidden engine behind reality itself. The twin paradox: imagine two twins who are identical in every way. They share the same birthday, the same childhood memories, and the same heartbeat rhythm. Now imagine that one of them boards a spaceship and embarks on a journey across the galaxy at nearly the speed of light, while the other stays on Earth. To the twin who remains, months turn into years, years into decades. But for the twin on the ship, time flows differently. When they finally return, the twin who traveled is much younger than the one who stayed behind. Both were born at the same moment, yet they no longer share the same age. This is the essence of the twin paradox, one of the most famous puzzles in Einstein's theory of relativity. At first, the paradox seems impossible. How can time flow at different speeds for different people? We are taught to believe that time is universal, that 1 second for you is 1 second for me, and 1 second for anyone else, no matter where they are. But relativity shows us that this is not true. Time is not absolute. It bends and stretches depending on motion and gravity, and the twin paradox is the perfect way to see this in action. Here's how it works. According to Einstein's special relativity, the faster you move, the slower time passes for you relative to someone at rest. This effect is called time dilation. At everyday speeds, the difference is too small to notice. But as you approach the speed of light, the effect becomes extreme. For the twin traveling at near light speed, days or months may pass on the ship, while years or centuries pass on Earth. When they finally return, they step off the spacecraft to find that their sibling has aged far beyond them. The paradox is not that time slows down. It's that each twin sees the other's clock ticking more slowly. So, how can both be right? This is where the puzzle deepens. From the perspective of the twin on Earth, the traveling twin's clock runs slow. But from the perspective of the traveling twin, it's the Earth twin's clock that runs slow. Each one believes the other is aging more slowly, and both cannot be correct. This seems like an impossible contradiction. The resolution comes from the fact that the two situations are not perfectly symmetrical. The Earth twin remains in one frame of reference, while the traveling twin accelerates, decelerates, turns around, and eventually returns. Those changes in motion break the symmetry. Relativity shows us that the traveling twin truly does experience less passage of time. When the twins reunite, the traveler is younger. This is not science fiction, it is reality, proven through experiments with atomic clocks flown on planes and satellites. Time dilation is real, measurable, and already affects the GPS satellites orbiting above Earth. Without correcting for relativity, your navigation system would drift miles off course every single day. But the twin paradox raises questions far deeper than navigation. It challenges our very sense of time. We like to imagine time as a universal river flowing steadily forward, carrying all of us along at the same pace. But relativity tells us that time is not a single river. It is more like a vast ocean, with currents flowing at different speeds depending on where you are and how you move. Two people can start together, travel apart, and meet again, yet their journeys through time are not the same. This leads to a profound realization. Time is personal. It is not the same for everyone. Each of us carries our own clock, ticking according to our own path through space and gravity. The twin paradox shows us that reality is not a single timeline shared by all, but a fabric where each thread stretches differently, woven together yet never identical. And then comes the more unsettling thought. If time can stretch and bend, if one person can age slower than another, then what does that mean for the future of humanity? Could we one day travel the stars, reaching distant galaxies within a single lifetime, while centuries pass back on Earth? Could explorers return to find Earth transformed, civilizations risen and fallen, while they themselves have barely aged? To travel through space in this sense is also to travel into the future. The twin paradox is not just about physics. It is about identity and separation. Imagine reuniting with your twin after such a journey. They are old, their face lined with time, their life nearly complete, and you, standing beside them, still young, still filled with years they will never see. You are bound by blood, yet torn apart by time. The paradox is not just in the equations. It is in the heartbreak of seeing the same origin lead to two very different destinies. In the end, the twin paradox reminds us of a truth we rarely consider. Time is not as steady as the ticking of a clock on the wall. It bends with speed, curves with gravity, and dances differently for each of us. To live is to move through time in a way no one else can fully share. The question is not whether time can split us apart. It already does. The real question is how far we are willing to go into the future, knowing we may never return to the time we left behind. The arrow of time, paradox. Why does time only move forward? Every day we wake up, watch the sun rise, grow older, and never once doubt the direction in which life flows. A glass slips from your hand, falls, and shatters into pieces. You can sweep up the shards, but you will never see them leap back together into a perfect glass. Milk spills, but never unspills. We remember the past, but never the future. This one-way direction of time is so deeply ingrained in our lives that we rarely question it. Yet, when we look closely at the laws of physics, something deeply unsettling emerges. The laws that govern particles, energy, and motion do not require time to flow in only one direction. The equations work just as well forward as they do backward. So, why does reality insist on moving only from past to future? This mystery is called the arrow of time paradox. At the heart of this paradox lies entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases over time. In simple terms, order naturally decays into disorder. A neat room becomes messy. A candle burns down to wax and smoke. Energy spreads, never concentrating back into its original form. This constant drift toward disorder gives time its arrow, pointing from order in the past toward chaos in the future. But here's the puzzle: the fundamental laws of physics, Newton's equations, Maxwell's equations, even the equations of quantum mechanics, are time-symmetric. They do not prefer forward over backward. If you filmed two colliding billiard balls and played the video in reverse, the motion would look perfectly natural. Physics doesn't care whether time moves forward or backward. So, why, in our lived experience, does time feel irreversible? Why can we remember what has happened, but never what will happen? Some scientists argue that the arrow of time is not built into the laws of physics themselves, but into the conditions of the universe. At the moment of the Big Bang, the universe began in a state of incredibly low entropy, a state of unimaginable order. As the cosmos expanded, disorder naturally increased, and time's arrow began to emerge. If the universe had started in chaos, perhaps time would not appear to flow at all. This suggests that our sense of time is not a fundamental law, but the result of a cosmic accident, a condition set at the birth of everything. But this raises an even deeper paradox. Why did the universe begin in such a state of order in the first place? What caused the Big Bang to set the initial conditions for time to flow forward? No one knows. It is one of the most profound mysteries in cosmology. Some suggest that time itself may have emerged at the Big Bang, with no before for entropy to increase from. Others wonder if multiple universes exist, each with its own arrow of time, some flowing forward like ours, others perhaps flowing backward from our perspective. The paradox also touches on consciousness. Our minds experience time as a flowing river, carrying us steadily from birth to death. But if the laws of physics allow for time to run in both directions, why do we only perceive one? Some philosophers argue that memory itself is tied to entropy. We remember the past because it was more ordered than the present. The future is unknowable not because it doesn't exist, but because it is more disordered. Our sense of moving through time may be nothing more than our awareness aligning itself with the increase of entropy. And yet, there are moments that make us wonder. In the equations of quantum mechanics, particles can sometimes behave in ways that appear to move backward in time. In the strange mathematics of black holes, time can bend, twist, or even stop. Physicists still debate whether the arrow of time is a deep truth of the universe or merely a feature of our perception. The arrow of time paradox is unsettling because it cuts at the heart of existence itself. Without a forward-moving arrow, what does it mean to live, to age, to die? Are these processes inevitable laws or illusions shaped by entropy and perspective? If time could run backward, would we even notice, or would our memories simply reverse, leaving us convinced that everything was still moving forward? Perhaps the arrow of time is not absolute but relative, just like motion and space. Perhaps in some far-off corner of the multiverse, another form of life experiences time flowing the opposite way, watching what we call the future unfold behind them. Or perhaps the arrow is a fragile illusion, one that will eventually break when entropy reaches its maximum, leaving the universe in a frozen, timeless state. The paradox forces us to confront a chilling possibility. The forward march of time, the most familiar aspect of our lives, may not be fundamental at all. It may be a temporary feature of the universe, born with the Big Bang and destined to end with the heat death of the cosmos. Until then, we move forward, carried on time's arrow like passengers on a one-way flight, unable to look back, unable to turn around, forever wondering why the arrow points where it does, and what will happen when it finally stops. The cosmic horizon paradox. When we look into the night sky, we are not just looking into space, we are looking into the past. Every point of light, every star, every galaxy sends its glow across vast distances, and the farther it travels, the older it becomes by the time it reaches us. But no matter how far we look, there is a limit to what we can see. Beyond a certain boundary, the light from distant objects has not had enough time to reach us since the birth of the universe. This invisible boundary is called the cosmic horizon, and here lies the paradox. If the universe is infinite, then there should be infinite stars and galaxies in every direction. So why can we only see a fraction of them? Why does the universe appear finite to our eyes, when in theory, it may stretch endlessly beyond? This puzzle is known as the cosmic horizon paradox. At first glance, the answer seems obvious. Light has a speed limit, 300,000 kilometers per second. And the universe has a finite age of about 13.8 billion years. Therefore, we should only be able to see objects within 13.8 billion light years of us. But this is where the paradox deepens. Because the universe is expanding, galaxies are being carried away from us faster than the speed of light. As a result, the observable universe is actually much larger, about 93 billion light-years across. Beyond this horizon, galaxies exist, but their light will never reach us. They are beyond observation forever, sealed away by the expansion of space itself. This creates a troubling thought. If there are galaxies we can never see, then our view of the universe is only partial, a tiny window in a much greater whole. The cosmos we observe may not be the cosmos as it truly is. The paradox, then, is not only about distance, it is about knowledge. Are we seeing reality, or just a small slice of it distorted by the limits of light and time? To make this more unsettling, consider the fact that the farther we look, the younger the universe appears. A galaxy at the edge of our cosmic horizon is not as it is today, but as it was billions of years ago when the first stars were still forming. We can never see these galaxies as they exist now. Their present reality is forever hidden because their light is always racing toward us from the past. In a sense, we are trapped in a paradox of perception. The universe we see is not the universe as it is, but the universe as it was. Some scientists argue that this means our universe has two realities, the observable universe and the unobservable universe. The observable is what we can detect, measure, and study. The unobservable is everything beyond the horizon, inaccessible to us in principle. If that is true, then our picture of the cosmos may always be incomplete. There could be vast structures, galaxies, or even laws of physics beyond our horizon that we will never know. Perhaps the constants of nature differ out there. Perhaps whole regions of space are governed by physics unlike anything we have discovered. And yet, for us, these places might as well not exist, because they will forever remain beyond the reach of light. This leads to even stranger possibilities. If the universe is infinite, then somewhere beyond our horizon, there may be galaxies identical to ours, stars identical to our sun, even versions of Earth indistinguishable from the one we live on. In an infinite expanse, every possible arrangement of matter must occur, and so the horizon may not only hide unknown galaxies, it may hide other versions of ourselves. And then comes the darker side of the paradox. If we are limited to seeing only within the cosmic horizon, then perhaps reality itself is shaped by those limits. Some cosmologists wonder whether the horizon defines not just what we can see, but what truly exists for us. If information can never cross that boundary, does it, in some sense, not exist at all? Is reality only as big as what can be observed? Or is the horizon just a wall hiding an endless cosmos that we can never touch? The cosmic horizon paradox forces us to confront the terrifying scale of our ignorance. We speak of the universe as if we understand it, but what we see is a cosmic bubble, a small fraction of an unfathomable whole. The horizon is a line not of distance, but of understanding, a reminder that beyond it lies something we can never know. And yet, within that ignorance lies possibility. If we cannot see beyond the horizon, then we cannot rule out what might be there. New physics, new laws, even new forms of reality itself. The paradox is both humbling and unsettling. It tells us that even as we map galaxies, measure cosmic background radiation, and peer into the earliest moments of time, we remain prisoners of perspective. The universe is larger, stranger, and more mysterious than anything our eyes, or our instruments, can ever reveal. Beyond the horizon, infinity waits, silent and unreachable. And perhaps the greatest paradox of all is this. The more we discover about the cosmos, the more it reminds us how little we truly know. Zeno's paradoxes. More than 2,000 years ago, a philosopher named Zeno of Elea posed a set of puzzles that continue to trouble minds today. They were simple thought experiments, but their implications reached into the very fabric of reality. Motion, time, and infinity itself. These are known as Zeno's paradoxes. And even though we live in an age of quantum physics and relativity, they still force us to question whether movement, change, and time are as straightforward as they appear. The most famous is Achilles and the tortoise. Imagine Achilles, the greatest Greek warrior, racing a tortoise. To make it fair, Achilles gives the tortoise a small head start. Now, when Achilles begins to run, he quickly reaches the point where the tortoise started. But by that time, the tortoise has already moved a little farther ahead. Achilles runs again to close the gap. But once more, the tortoise has inched forward. No matter how fast Achilles runs, the tortoise always stays slightly ahead. Because each time Achilles reaches where the tortoise was, the tortoise has moved to a new spot. By this reasoning, Achilles can never overtake the tortoise. Motion itself seems impossible. Then there is the dichotomy paradox. To reach any destinations, you must first travel halfway there, and before that, you must travel halfway to halfway, and again, halfway to halfway to halfway. The journey can be divided infinitely into smaller and smaller steps. If there are infinite steps to take, how can you ever arrive at your destination? Movement requires completing an infinite number of tasks, which seems impossible. Yet in everyday life, we walk across rooms and travel miles without hesitation. How can this be? Zeno's arrow paradox pushes even further. Picture an arrow flying through the air. At any given instant, if you freeze time, the arrow is motionless, occupying a single space. If at every instant the arrow is not moving, then how does motion ever occur? Time seems to break down into snapshots of stillness, yet somehow, strung together, these still moments create motion. Is movement real, or just an illusion created by our perception of time flowing? These paradoxes may sound like tricks of logic, but they reveal a much deeper mystery: infinity. Zeno showed that when you divide time and space into infinite parts, contradictions emerge. Our minds can imagine infinite divisions, but our reality insists that things happen in finite, measurable ways. Achilles easily outruns the tortoise in the real world, yet Zeno's logic suggests he never should. So, which is true, our intuition of movement or the logic of infinity? For centuries, philosophers debated these puzzles, until mathematics provided an answer through the invention of calculus. Calculus showed that infinite series can add up to finite sums. Achilles can cover infinitely many halves, because the distances get smaller and smaller, and the total adds up to a limit. In the tortoise race, the infinite steps Achilles must take shrink so quickly that he overtakes the tortoise in finite time. Motion, it turns out, is possible even when divided into infinity. Yet, even with this solution, Zeno's paradoxes continue to haunt us. In modern physics, space and time may not be infinitely divisible. At the smallest scales, near the Planck length and Planck time, divisions may stop, and reality may come in discrete units, like pixels on a screen. If this is true, then Zeno was pointing toward a fundamental truth. Perhaps infinity itself is an illusion, or perhaps reality really is continuous, and infinity exists within every step and every moment. And then there is the psychological dimension. The arrow paradox echoes in our experience of time. Each instant of our lives feels like a frozen snapshot, yet strung together, they create the story of who we are. Are we truly moving forward, or are we simply perceiving an endless series of still frames? If so, then time may not flow. It may be a collection of instants that our consciousness stitches together into motion. Zeno's paradoxes are not just clever riddles, they are cracks in the foundations of how we think about space, time, and reality. They remind us that the simplest acts, walking, running, watching an arrow fly, contain mysteries as deep as the universe itself. Motion, which feels so obvious, may be one of the greatest illusions of all. So the next time you take a step forward, remember Zeno. Ask yourself, did you really move, or did you simply cross an infinite chain of halves, each step containing infinity within it? Perhaps every stride, every heartbeat, every moment of your life is a paradox in disguise, reminding you that reality is stranger than it seems. The infinite hotel paradox: imagine a hotel that is infinitely large. It has an endless number of rooms, stretching on forever in both directions, each one already occupied by a guest. At first glance, you'd think such a hotel could never accept new arrivals. It's already full. Yet, here's the paradox. Not only can the infinite hotel always accommodate new guests, but it can also make space for infinitely many more. This strange idea, known as Hilbert's Hotel or the Infinite Hotel Paradox, challenges our understanding of infinity and what it means to be full. Here's how it works. Suppose a new guest arrives at the hotel. The manager thinks for a moment, then tells every guest to move from their current room to the next one. Room 1 goes to room 2 goes to room 3, and so on, all the way to infinity. Since there's no last room, this process never ends, and suddenly, room 1 becomes available. Even though the hotel was already full, it has made space for one more guest. Now imagine not just one guest, but an entire bus of infinite new guests arriving. Can the hotel take them in? Strangely, yes. The manager simply asks each current guest to move to the room numbered double their current one. Room 1 goes to room 2, room 2 goes to room 4, room 3 goes to room 6, and so on. Now, every odd-numbered room is empty, an infinite number of rooms for an infinite number of new arrivals. The hotel never runs out of space, no matter how many guests come knocking. This paradox reveals something unsettling. Infinity is not like any number we know. A finite hotel that is full has no room left. But an infinite hotel that is full still has room for infinitely more. Infinity defies the rules of arithmetic, twisting our intuition into knots. But it gets stranger. Suppose an infinite number of buses, each carrying an infinite number of guests, arrives at the same time. Surely this must be too, even for an infinite hotel. But no, the manager has a trick. He can assign each guest a unique room by using clever patterns of numbering, such as prime factors or squares. The paradox shows that infinity is not just endless, but layered and structured in ways that stretch the limits of imagination. This puzzle was introduced by the mathematician David Hilbert, not as a real hotel, but as a way to illustrate the bizarre properties of infinity. It forces us to ask, can infinity ever be truly understood, or is it forever beyond the grasp of human logic? The infinite hotel paradox also has deeper implications in physics and cosmology. If the universe is infinite, then space itself may behave like Hilbert's hotel. There could always be room for more matter, more galaxies, more energy. Some theories even suggest that multiple universes might exist, stacked in infinite layers beyond our reach, raising the question of whether infinity is not just an idea, but a physical reality. The paradox also challenges our ideas of existence itself. If infinity allows endless rearrangement, then perhaps every possible arrangement of reality exists somewhere. Every possible world, every possible version of you, living in some infinite room of existence. Infinity, in this view, is not just big, it is everything. But the infinite hotel also reminds us of the limits of human thought. Our minds evolved to count sheep, coins, and days, not to wrestle with infinities. When we try, logic begins to break. A hotel that is full, yet has room for more. A structure where subtraction and addition no longer follow familiar rules. A place where infinity is not just endless, but endlessly strange. In the end, Hilbert's hotel is not about rooms or guests. It is about the nature of reality. If infinity exists, then our most basic intuitions about space, time, and existence may be wrong. Infinity is not just a number beyond counting. It is a force that bends logic, reshapes mathematics, and whispers to us that the universe may be far stranger and far larger than we can ever truly comprehend. So next time you look into the night sky and imagine the stars going on forever, remember the infinite hotel. In that endless expanse, there is always room for more stars, more worlds, more possibilities, and perhaps more versions of yourself than you could ever imagine. The Banach-Tarski Paradox. Imagine holding a simple, solid ball in your hands. It feels ordinary, finite, and bound by the rules of common sense. But now, imagine cutting that ball into a handful of pieces, rearranging them, and suddenly ending up with not one, but two balls identical to the first. You didn't add any material, you didn't stretch anything, you didn't create something from nothing, you just moved the pieces around. This is the essence of the Banach-Tarski Paradox, a mind-bending idea that suggests infinity can make the impossible possible. At first, it sounds like a magician's trick, or outright nonsense. How can you create two whole objects from one without shrinking or duplicating? Yet, mathematically, the paradox is perfectly valid. In the early 20th century, two Polish mathematicians, Stefan Banach and Alfred Tarski, proved that under certain conditions, this is not only possible, but inevitable. The trick lies in how infinity and geometry interact. The paradox depends on something called the axiom of choice, a principle in mathematics that allows us to select elements from infinite sets, even when there is no clear rule for choosing them. Using this axiom, Banach and Tarski showed that a sphere can be divided into a finite number of extremely strange, infinitely complicated pieces. These pieces are not like slices of an orange or chunks of wood. They are so fractured, so fragmented, that they cannot be visualized in ordinary space. They are like dust made of infinity, scattered beyond comprehension. And yet, when rearranged, these bizarre fragments can form not just one sphere, but two spheres identical in size to the original. What's more, the paradox doesn't stop there. Using the same method, you could create 3 spheres, 4 spheres, or infinitely many spheres, all the same size as the one you started with. Out of one finite ball, you could create endless copies. In pure mathematics, this is perfectly consistent. But in the world we live in, it feels like a violation of the most basic law of existence, that you cannot get something from nothing. Of course, the Banach-Tarski paradox does not mean you can actually duplicate a physical ball in reality. The process depends on treating matter as infinitely divisible, down to levels smaller than atoms, smaller than particles, smaller even than the Planck length, the fundamental limits of physics. In our universe, you cannot break matter apart infinitely because atoms are not infinitely divisible. The paradox lives in the realm of abstract mathematics, not in physical reality. Yet, its implications are unsettling. If pure logic can lead to such an impossible conclusion, what does that say about the nature of infinity? The paradox also forces us to rethink the idea of volume and space. When we measure the size of an object, we assume that volume is a fixed property. But in Banach-Tarski's strange universe, volume becomes slippery, inconsistent, and dependent on how you rearrange infinity. It shows that infinity does not behave like the finite numbers we use in everyday life. It follows its own rules, rules that can create entire worlds out of fragments. Some philosophers see this paradox as more than a mathematical curiosity. They see it as a window into the strangeness of existence itself. Could the universe, at its deepest levels, operate by rules that defy our intuition of matter and space? Could reality itself be divisible and reconstructible in ways we cannot yet imagine? If mathematics allows something so counterintuitive, perhaps nature itself is stranger than our senses suggest. The Banach-Tarski Paradox also echoes with ancient ideas about creation and destruction. From nothing, something arises. From one, many. It is almost a mathematical reflection of myths where gods split a single source into the world we know. Except here, it is not myth, but the raw logic of infinity that allows creation from division. In the end, the Banach-Tarski Paradox is not about splitting spheres. It is about the nature of infinity and the limits of human reason. It reminds us that infinity is not just big, it is alien, unsettling, and endlessly deceptive. Infinity does not follow our rules, it rewrites them. And in that rewriting, it shows us that the boundaries of logic and reality are far wider and far stranger than we dare to imagine. So the next time you hold something solid, something finite, in your hands, consider this. In the strange world of infinity, even the most ordinary object might hide impossible possibilities. An entire infinity waiting to be released. Russell's paradox, at first glance, logic feels safe. It is the foundation of mathematics, the bedrock of reason. If numbers are solid, then sets, the groups that contain them, seem even more reliable. A set can be simple, like the set of even numbers, or complex, like the set of all prime numbers greater than 100. But in 1901, the philosopher and mathematician Bertrand Russell discovered something deeply unsettling. The very concept of sets can collapse into contradiction. This is known as Russell's paradox, and it shook the foundations of mathematics to their core. Here's the idea. Imagine a village where some barbers shave themselves and others do not. Now, suppose there is one special barber, the barber who shaves everyone who does not shave themselves. The question is simple. Does the barber shave himself? If he does, then by definition, he should not shave himself, because he only shaves those who don't. But if he doesn't shave himself, then he falls into the group of people who must be shaved by the barber, which means he must shave himself. Either way, contradiction arises. This little riddle is a metaphor for Russell's discovery about sets. In mathematics, you can define sets based on rules. For example, the set of all red objects, or the set of all numbers greater than 10. But what about the set of all sets that do not contain themselves? Does such a set contain itself? If it does, then it shouldn't. If it doesn't, then it must. The contradiction cannot be resolved. Logic folds in on itself, and mathematics begins to tremble at its foundations. Before Russell, mathematicians believed that set theory, the study of collections of objects, was a flawless language for building all of mathematics. But Russell's paradox showed that naive set theory, the version used at the time, was inconsistent. If left unchecked, it allowed contradictions to arise and contradictions in logic are catastrophic. In mathematics, one contradiction can unravel everything, because from a contradiction you can technically prove anything, even absurdities. It was as if the foundation stone of the mathematical universe had cracked. The discovery forced mathematicians to rethink their entire system. Some developed stricter rules for how sets could be defined, such as Zermelo-Fraenkel set theory, which carefully avoids the kind of self-reference that causes paradoxes. Others turned to different foundations altogether, exploring systems of logic designed to avoid self-contradiction. In this way, Russell's paradox reshaped modern mathematics, ensuring that its foundation would be more secure. But beyond mathematics, the paradox raises deeper philosophical questions. Self-reference, things that refer back to themselves, is at the heart of many human puzzles. Think of the statement, "This sentence is false. If it is true, then it must be false. If it is false, then it must be true." Russell's paradox is part of this family of puzzles, where systems collapse when they try to include themselves. It reveals the limits of formal systems, showing us that even the most precise logic can break when caught in a loop of self-reference. This echoes in many areas of life. In language, we stumble on contradictions like, "I always lie." In law, we encounter rules about rules that generate conflicts. In consciousness, the mind tries to understand itself, creating endless spirals of self-reflection. Russell's paradox is more than mathematics. It is a mirror of the strange and unstable nature of self-referential thought. Some philosophers even suggest that paradox is not an error, but a clue. Perhaps self-reference is not a flaw to be avoided, but a fundamental part of reality. Our universe itself may be self-contained, referring back to itself like a loop. Consciousness may be a self-referential system, aware of itself being aware. In this sense, Russell's paradox is not just a mathematical trap. It is a window into the very structure of existence. In the end, Russell's paradox reminds us that no system is immune to contradiction. The moment we believe we have built something perfect and airtight, a paradox emerges to show us its cracks. Logic, like life, is never complete. There will always be boundaries where certainty breaks and mystery begins. So the next time you think about rules, categories, or definitions, remember Russell's question. What about the set of all sets that do not contain themselves? The paradox lies not in the answer, but in the asking. It is a reminder that even in the most rigid structures of thought, infinity and self-reference will always find a way to unsettle certainty, and remind us that truth is often more fragile and more mysterious than it seems. The liar paradox. Imagine someone looking you in the eyes and calmly saying, "I am lying." You pause, waiting for the punchline, but none comes. The sentence hangs in the air, ordinary yet impossible. If the statement is true, then the person really is lying, which means the statement must be false. But if it is false, then they are not lying, which means the statement must be true. Both possibilities cancel each other out, leaving you trapped in a loop with no escape. This is the heart of the liar paradox, a puzzle so simple in words, yet so devastating in meaning that it has haunted philosophy and logic for over 2,000 years. The paradox is often credited to the Greek philosopher Epimenides, who declared, "All Cretans are liars," while he himself was a Cretan. If his statement was true, then he must also be lying. But if he was lying, then perhaps not all Cretans are liars. Like a snake swallowing its own tail, the sentence folds in on itself, consuming both truth and falsehood until nothing remains but contradiction. At its core, the liar paradox is about self-reference, a statement that points back at itself. Normally, language works because statements describe things outside themselves. The sky is blue points to the sky. 2 + 2 is 4 points to numbers. But when language begins describing itself, when a sentence turns its gaze inward, the rules collapse. The statement becomes both true and false at once, and logic has no way to resolve it. For centuries, philosophers and logicians struggled with the liar paradox. Some dismissed it as a linguistic trick, a meaningless tangle of words. Others saw it as a profound clue to the limits of truth itself. If language allows for statements that cannot be classified as true or false, then maybe truth is not as absolute as we think. Perhaps some statements exist outside the boundaries of truth and falsehood, in a twilight zone where logic cannot follow. The paradox also influenced mathematics and computer science in unexpected ways. In the 20th century, Kurt Gödel developed his Incompleteness theorems, which showed that in any formal mathematical system, there are always true statements that cannot be proven within that system. Gödel's method relied on a kind of self-reference, statements that refer to themselves in a way similar to the liar paradox. His discovery shook mathematics just as Epimenides' sentence shook philosophy. Both revealed that no system of logic can be complete because self-reference always creates cracks in its foundation. In computer science, the same problem arises when machines try to process self-referential instructions. For example, consider a program that is told to analyze itself and determine whether it will stop running or continue forever. This problem, known as the halting problem, is unsolvable in general. It echoes the same infinite loop of contradiction found in the liar paradox. But beyond philosophy, mathematics, and machines, the liar paradox touches something deeply human: consciousness. When we reflect on ourselves, when the mind turns inward to analyze itself, it creates loops that never fully resolve. Am I truly aware, or only aware of being aware? This endless layering of self-reference is the very structure of thought, and like the liar paradox, it cannot be resolved by simple logic. Perhaps our own consciousness is, in a way, a living paradox. The liar paradox also reveals the fragility of truth in everyday life. In conversation, we rely on trust that words can be judged true or false, but the paradox shows that language itself can generate contradictions that cannot be untangled. In a world filled with misinformation, half-truths, and deliberate lies, the liar paradox serves as a haunting reminder. Truth is not always clear, and so, times the very act of questioning it can collapse certainty. So, what do we do with a paradox that cannot be solved? Some logicians propose a third category of truth, statements that are neither true nor false, but something else entirely. Others suggest the paradox reveals that our systems of logic must always remain incomplete, because reality is not as neatly divided as we hope. And still others embrace it as a reminder of mystery, that in language, as in life, not every knot can be untied. The liar paradox is more than a clever riddle. It is a mirror held up to the human mind, showing us both the power and the limits of reason. It whispers that truth is not a simple binary, but a shifting landscape where self-reference creates endless loops. And in those loops, perhaps, lies the essence of paradox itself, the reminder that the closer we come to certainty, the more we discover the infinite shadows hidden within. The missing dollar paradox. Imagine three friends walk into a hotel, tired after a long journey. They decide to share a room that costs $30. Each one contributes $10, handing the total $30 to the hotel clerk. A few minutes later, the manager realizes there has been a mistake. The room is actually on discount and should cost only $20. Wanting to fix the error, the manager gives $5 to the bellboy and asks him to return it to the guests. But the bellboy faces a dilemma. He cannot split $5 evenly among 3 people, so he decides to give each guest $1 back and quietly keep $2 for himself. Each friend now has paid $9 instead of $10, so together they paid $27. Add the $2 the bellboy kept, and it seems the total is $29. But wait, what happened to the missing dollar? This little puzzle is the essence of the missing dollar paradox, a problem that has confused generations of readers, students, and thinkers. At first glance, it looks like a simple arithmetic trick gone wrong, but the paradox lies not in the math itself, but in how we frame the situation. Let's slow down and examine carefully. The friends originally paid $30. The room ended up costing $25, which means they should get $4 back. They each received $1 for a total of $3 returned, and the bellboy kept $2. That adds up to $25 room plus 3 guests' refunds plus 2 bellboy's pocket. It's $30. Nothing is missing. The lost dollar appears only because we added the wrong numbers together. 27, what the guests paid after refunds, already includes the $2 for the room and the 2 kept by the bellboy. Adding another $2 is double counting. So the paradox is not a failure of mathematics. It is a failure of reasoning. The trick works because our minds are quick to accept the framing of the puzzle. The problem directs us to look for a missing dollar, so we begin searching for it, when in fact there was never a dollar missing in the FE. Rest place. It is an illusion of logic, a reminder that the way a problem is presented can shape the way we think about it. But the missing dollar paradox is more than a clever riddle. It is a window into the psychology of perception. Humans are deeply influenced by framing effects. If numbers are arranged in a misleading way, or if a story is told with a particular emphasis, we often overlook the simple truth. The paradox shows how easily our reasoning can be guided into a trap, not because we lack intelligence, but because our minds are wired to follow the path that language and context set for us. This has profound implications. In everyday life, the same kind of missing dollar illusion happens when we look at statistics, prices, or deals. A product advertised as 20% off, then an additional 10% off sounds like a 30% discount, but it isn't. A politician may present numbers in a way that looks convincing, yet hides the real story. A magician uses misdirection not just with objects, but with words, leading your mind to chase what isn't missing. The missing dollar paradox, then, is not just about money. It is about how easily our perception of reality can be manipulated. There is also a deeper, almost philosophical angle. The paradox forces us to question whether truth is always in the numbers or in how we interpret them. The math never lied. 30 was always accounted for. What misled us was the narrative we built around the math. In this sense, the paradox reflects a broader truth about life. Reality is not just facts, but the story we tell about those facts. When the story is misleading, even the clearest numbers can seem paradoxical. And perhaps that is why the missing dollar paradox has lasted so long. It is not just a puzzle to amuse children or trick tired students. It is a mirror held up to human thought. It shows that even in something as solid as arithmetic, misunderstanding and illusion can creep in, making us believe in losses that don't exist and mysteries that were never there. In the end, the missing dollar never existed. What was missing was clarity, and in that realization lies the true lesson of the paradox. Numbers are only as trustworthy as the stories we attach to them. The Monty Hall Paradox. Imagine you are on a game show. In front of you are 3 closed doors. Behind one door is a brand new car. Behind the other 2 doors are goats. The rules are simple. Pick a door, and whatever is behind it is yours. You choose door No. 1, feeling lucky. The host, Monty Hall, who knows what is behind every door, then opens another, say, door No. 3, revealing a goat. Now comes the twist. Monty gives you a choice. Do you stay with your original door, or switch to the other unopened door, door No. 2? At first glance, it seems like it doesn't matter. There are 2 doors left, one with a car and one with a goat, so the odds feel 50-50. Many contestants in real life chose to stay with their first pick. But mathematics reveals something shocking. The odds are not even. If you switch, your chance of winning jumps to 2 out of 3. If you stay, your chance is only 1 out of 3. This strange counterintuitive result is the heart of the Monty Hall Paradox. Why is this the case? Let's break it down. When you first pick a door, you have a 1 in 3 chance of being right. That means there's a 2 in 3 chance that the car is behind one of the other 2 doors. When Monty opens a door to reveal a goat, he isn't choosing at random. He knows where the car is and always avoids it. By eliminating one wrong option, he shifts the odds. The full 2 in 3 chance now rests on the unopened door. Switching, therefore, doubles your odds of winning. But this reasoning feels wrong to most people. Our intuition tells us that once a door is opened, the game resets, leaving a simple coin flip between the 2 remaining doors. The paradox exposes a deep gap between human intuition and mathematical reality. In fact, when this problem was popularized in the 90s by columnist Marilyn Vos-Savant, thousands of readers, including many mathematicians, insisted that she was wrong to suggest switching. But repeated experiments and simulations prove the math correct. Switching gives you the advantage. The Monty Hall Paradox is more than just a puzzle. It is a lesson in probability and human psychology. We are naturally bad at judging odds when hidden information is involved. Our minds crave simplicity, so we assume equal chances where none exist. The paradox teaches us that in life, as in the game show, unseen structures can shape outcomes in ways our intuition misses. This problem also mirrors real-world situations. Consider medical testing. A person might test positive for a rare disease, and intuition might suggest they almost certainly have it, but probability tells a different story. If the disease is rare and the test is imperfect, the odds may actually be much lower than we think. Similarly, in business, risk-taking, or even gambling, misunderstanding probability can lead us to make poor choices, believing situations are fair or random when hidden patterns tilt the odds. The Monty Hall Paradox also reveals something about decision-making under uncertainty. Many players stick with their original choice out of a sense of loyalty or fear of regret. If they switch and lose, they blame themselves for second-guessing. If they stay and lose, they feel it was simply bad luck. This shows how emotion often outweighs logic in human choices. The paradox, then, is not just about doors, cars, and goats. It is about how we handle risk, trust, and uncertainty. In the end, the Monty Hall Paradox is not just a quirky game show trick. It is a reminder that reality often hides deeper structures beneath the surface. Probability is not always intuitive, and our instincts can mislead us. Sometimes, the smartest move in life is the one that feels least natural, to let go of your first choice, to embrace the counterintuitive, and to recognize that behind the doors of uncertainty, mathematics often has the final word. Gödel's Incompleteness Theorem. For centuries, mathematicians dreamed of building a perfect system of logic, a foundation so strong that every truth could be proven, every question answered, every doubt erased. Mathematics seemed to be the language of certainty, the one place where human reason could not be shaken. But in 1931, a quiet Austrian logician named Kurt Gödel shattered that dream. With a single stroke of genius, he proved that no matter how strong, no matter how carefully built, every mathematical system contains truths that cannot be proven within its own rules. This is the heart of Gödel's Incompleteness Theorem, one of the most unsettling paradoxes ever discovered in human thought. To understand it, imagine a book that contains all the rules of mathematics, axioms, formulas, and proofs. In theory, with enough time, you should be able to use that book to prove every mathematical statement that is true. But Gödel asked a haunting question. What if there are true statements that cannot be proven using the system itself? To answer it, he constructed a self-referential sentence, similar to the liar paradox. It was essentially a statement that said, this statement cannot be proven. If the system could prove the statement, then it would be false, because the statement claims it cannot be proven. But if the system cannot prove it, then the statement is true. There exists a true mathematical statement that the system cannot prove. Either way, completeness is lost. No logical system can prove all truths about itself. This was revolutionary. Before Gödel, great minds like Hilbert believed in the possibility of a complete and consistent foundation for all of mathematics. Gödel's theorem showed that this dream was impossible. Mathematics, once thought to be the perfect fortress of certainty, was revealed to be limited. There will always be truths that exist outside the walls of proof, truths that we can see but cannot reach. But Gödel did not stop there. His work also proved a second incompleteness theorem, that no consistent system can prove its own consistency. In other words, mathematics can never prove beyond doubt that it is free of contradictions. The fortress cannot guarantee its own strength. There is always a shadow of uncertainty, no matter how high the walls. The implications were enormous. Mathematics was no longer a closed book. It was an open, unfinished story. Logic itself had boundaries. The idea that reason could solve everything, that human minds could capture all truth through rules and proofs, collapsed under Gödel's insight. The paradox of incompleteness became a permanent scar on the dream of absolute certainty. This discovery rippled far beyond mathematics. In philosophy, Gödel's theorems revealed the limits of human knowledge. If no system can contain all truth, then perhaps reality itself will always remain partly unknowable. In computer science, Gödel's ideas inspired Alan Turing, who proved the halting problem, that no computer can predict in all cases whether another program will ever stop running. This limitation echoes Gödel's result. No machine of logic can capture all possible truths. Even in the study of the mind, Gödel's theorem raises haunting questions. Some argue that human consciousness must go beyond mechanical logic, since we can see truths that no formal system can prove. Others argue the opposite, that even our thoughts are bound by the same limitations, that the human mind, too, is incomplete. What makes Gödel's theorem so unsettling is not just its technical brilliance, but its existential weight. It reminds us that certainty is an illusion. No matter how much we prove, how much we know, there will always be truths just beyond reach, truths we can sense but never capture, like the horizon, that recedes as we approach it. Knowledge expands endlessly but never completes itself. Gödel's incompleteness theorem is not a failure of logic. It is a revelation about the nature of truth. Truth is larger than proof. Reality is larger than reason. There will always be mysteries that no system can contain, and perhaps this is not a weakness, but a kind of beauty. The universe reminding us that no fortress of logic can hold infinity, no book can contain all truths, and no mind can fully map the infinite. In the end, Gödel showed us something profound. The search for truth is endless. We will never reach the final page of the book of knowledge, because the book has no final page. And maybe that is the paradox that defines us. Not that we are incomplete, but that our incompleteness is the very thing that drives us forward, forever searching. The infinite monkey theorem. Picture a monkey sitting at a typewriter, pressing keys at random. At first, the pages would be nonsense. Letters scrambled without meaning, words broken apart, gibberish strung endlessly. But now, imagine not just one monkey, but an infinite number of monkeys, typing for an infinite amount of time. The infinite monkey theorem tells us that, given enough time, those random keystrokes will eventually produce every possible text. Hidden in the chaos would be the works of Shakespeare, the Bible, the code for modern computers, and even the very sentence you are reading now. At its heart, the theorem is about probability. Given infinite time, every possible sequence of letters must eventually appear. The odds of a monkey typing out a single line of Shakespeare correctly in one attempt are astronomically small, close to impossible. But infinity changes everything. With infinite attempts, what is nearly impossible becomes inevitable. Somewhere, in the endless sea of nonsense, masterpieces emerge. This thought experiment forces us to grapple with the strange nature of infinity. Our human intuition is built for finite things. We think in terms of days, years, lifetimes. Infinity, by contrast, is vast beyond comprehension. It turns impossibility into certainty. If you roll dice forever, every possible combination will appear infinitely many times. If monkeys type forever, every book that can be written already exists within the storm of randomness. Infinity is not just endless, it is exhaustive. But there's a deeper paradox here. Yes, infinity guarantees that meaning will appear, but it also guarantees that it will be drowned in noise. For every copy of Hamlet typed by chance, there will be an infinite number of meaningless pages filled with near misses, typos, and broken words. Truth becomes indistinguishable from error, creation from chaos, the infinite. Monkey theorem shows us that order does not vanish in randomness. It hides inside it, buried in infinite noise. This idea is not just philosophy, it echoes in modern science. In physics, some theories of the universe suggest an infinite cosmos, with infinite stars and infinite worlds. If that is true, then somewhere out there are exact copies of our Earth and exact copies of you, simply because, given infinity, every arrangement of matter must repeat. The theorem is not just about monkeys and typewriters. It is about the haunting possibility that infinity itself ensures duplication, inevitability, and endless repetition. It also touches on evolution and creativity. Some critics once mocked Darwin's theory of natural selection by saying life was as unlikely as monkeys typing Shakespeare. But this misses the point. Evolution is not random typing. It is shaped by selection, feedback, and survival. Where randomness produces infinite noise, evolution sculpts it into patterns. The infinite monkey theorem, then, becomes a contrast. Randomness alone produces everything but buries it in chaos, while guided processes carve meaning out of chance. In a way, the theorem is also a metaphor for the human mind. Our thoughts, at times, feel random, scattered like keys struck by a monkey. But out of that chaos, patterns emerge, ideas, stories, works of art. Perhaps creativity itself is like an infinite monkey, endless combinations of thought, with meaning arising from the rare patterns that resonate. Yet, there's also a darker undertone. If infinity contains everything, then it also contains everything terrible, every nightmare, every mistake, every horror repeated endlessly. Infinity is not just wonder, it is also weight. To imagine it fully is to realize that everything you fear, everything you regret, exists infinitely many times in an infinite cosmos. The infinite monkey theorem, then, is not just a quirky thought experiment. It is a doorway into the nature of chance, infinity, and meaning. It reminds us that in a universe of infinite possibilities, every story exists, not because of destiny, but because infinity demands it. Every word you speak, every choice you make, every life you live, it all exists somewhere, again and again, among the monkeys of eternity. So the next time you see a keyboard, imagine an infinite chorus of monkeys pressing the keys forever. Somewhere, in their endless typing, is your story already written, waiting to be found. And perhaps the true paradox is this. In the chaos of infinity, meaning is not lost. It is inevitable. Newcomb's Paradox. Imagine walking into a room where a strange game is about to begin. On a table sit two boxes. The first box, transparent, contains 1,000. The second box, opaque, may contain either 1,000,000 or nothing at all. You are given a choice. Take both boxes, the transparent one with 1,000 and the opaque one, whatever it holds. Or take only the opaque box, trusting that it contains the 1,000,000. Here's the twist. The game involves a super-intelligent predictor, almost perfect in accuracy, who has already anticipated your decision. If the predictor foresaw that you would take both boxes, it left the opaque one empty. If it foresaw that you would take only the opaque box, it placed 1,000,000 inside. You cannot fool the predictor. It has been right countless times before. Now, you must choose. Do you walk away with both boxes, or trust the opaque one alone? This is the dilemma of Newcomb's paradox, one of the most famous problems in decision theory. At first glance, the answer seems obvious. Why not take both? After all, no matter what is inside the opaque box, you gain an extra 1,000 by adding in the transparent box. This line of thinking is called the dominance principle. Taking more is always better. But wait, if the predictor is nearly perfect, then your choice was already anticipated. If you decide to take both boxes, the predictor would have known that and left the opaque one empty. If you take only the opaque box, the predictor would have known that as well and left 1,000,000 inside. In this view, called expected utility reasoning, the best move is to take only the opaque box. History shows the predictor almost never fails, so trusting it maximizes your reward. And so the paradox emerges. Both lines of reasoning seem airtight, yet they lead to opposite decisions. Do you take both boxes, following logic that says something is always better than new thing? Or do you take only one, trusting the predictive power that has never been wrong? The brilliance of Newcomb's paradox is that it touches on the deepest philosophical questions: free will, determinism, and the nature of choice. If the predictor truly knows your decision in advance, then are you really free to choose at all? Is your decision already written, waiting for you to discover it? Or is the predictor's success based only on probability, meaning your choice can still bend the outcome? This puzzle has split philosophers and mathematicians for decades. Some, known as two-boxers, argue that rationality means taking both, since your choice cannot change what is already in the opaque box. Others, known as one-boxers, argue that rationality means trusting the predictor, since the predictor's accuracy means your choice is linked to what's inside. Both sides insist they are right, and yet the paradox refuses to be resolved. Beyond philosophy, Newcomb's paradox echoes real-world problems. In economics, decision-making often involves predicting how others will act. In politics, strategies hinge on anticipating future moves. Even in personal life, trust plays a role. Do you act based on what you see now, or based on the hidden consequences that might already be set in motion? The paradox forces us to confront how much of our future is shaped by our choices and how much is already decided by forces beyond us. There is also a psychological angle. Many people take both boxes not because of logic, but because of fear. Fear of missing out on the visible 1,000. Others take only one because of trust. Trust that surrendering the small prize unlocks the greater reward. In this way, the paradox mirrors human life itself. Often we must choose between short-term gains and long-term possibilities, between visible certainty and hidden potential. Some have even compared the predictor to the universe itself. If reality is deterministic, if the laws of physics unfold with perfect precision, then perhaps all our choices are already predicted, just like in Newcomb's paradox. In that case, free will may be an illusion, a story we tell ourselves while the script is already written. On the other hand, if uncertainty and randomness truly exist, then perhaps the predictor can never be perfect, and our freedom is real. In the end, Newcomb's paradox does not tell us which choice is right. Instead, it forces us to see the tension between freedom and inevitability, between logic and trust, between the seen and the unseen. Whether you walk away with two boxes or one, the true prize of the paradox is not money. It is the unsettling glimpse into the nature of choice itself. So, if you were standing before those boxes right now, what would you do? Would you grab both and trust your own reasoning, or take only one and trust the predictor? That is Newcomb's challenge, and your answer says more about how you see the world than about the game itself. The ship of Theseus paradox. Imagine a legendary ship preserved in honor of its hero, Theseus. Over time, the wooden planks begin to rot, so one by one, they are replaced with new planks. Decades pass, and eventually every single piece of wood, the sails, the mast, the hull, has been replaced. The ship still looks the same, it sails the same seas, it carries the same name. But here's the haunting question. Is it still the same ship of Theseus? This puzzle, known as the Ship of Theseus paradox, strikes at the core of identity and change. If something has all of its parts replaced over time, is it still the same thing, or has it become something new entirely? The paradox becomes even stranger when we add another twist. Imagine that all the old planks that were removed from the ship are gathered, repaired, and reassembled into a second vessel. Now, which one is the real Ship of Theseus? The one with new parts but continuous history, or the one built from the original wood but newly assembled? Both claims feel right, yet they contradict each other. This paradox is not just about ships, it is about us. Human beings are constantly changing. Cells die and regenerate, memories fade, personalities evolve. Biologists tell us that most of the cells in our body are replaced within a decade. If every part of you has been renewed, are you still the same person who was born years ago? If your body and even your mind change, what holds your identity together? Philosophers have wrestled with this question for centuries. Some argue that identity lies in continuity, the unbroken chain of existence, the story of how one thing becomes another over time. By this view, the ship with the new planks is still the true Ship of Theseus because it carried the same journey forward. Others argue that identity lies in material essence, the physical stuff. By that view, the ship rebuilt from the original, wood is the real one because it contains the authentic material. But perhaps the paradox shows that identity is not absolute at all. Maybe the question, which is the real ship, has no single answer because identity is not fixed, it is fluid, shaped by perspective. The same is true of people. Are you the same person you were as a child? In some ways, yes. In others, no. You are both continuous and new, both original and rebuilt. The Ship of Theseus also touches on technology and modern life. Consider artificial intelligence, where parts of a program are constantly updated. Is it still the same AI or a new one each time? Consider medicine, where organ transplants, prosthetics, and even future brain uploads may replace parts of our body and mind. At what point do we stop being ourselves? The paradox, once about a mythical ship, now speaks directly to the future of human identity. There is also a spiritual angle. Some traditions teach that the self is not tied to the body or the mind, but to something deeper, the soul, the continuity of consciousness. From that perspective, even if every cell and thought changes, something essential remains untouched. The paradox, then, becomes a mirror reflecting back our beliefs about what we truly are. In the end, the Ship of Theseus paradox does not give us a neat answer. Instead, it asks us to reflect on the mystery of identity. We are all ships sailing through time, losing and gaining parts, remade again and again. Yet somehow, we still say, "This is me." Perhaps identity is not in the parts, nor in the materials, but in the story, the journey that ties all the changes together into a single thread. So, is the Ship of Theseus still the same ship? Maybe the better question is, when you look in the mirror and see a self that has changed over the years, are you still the same person? The paradox whispers yes and no. Both are true, and neither is complete. The brain in a vat. Imagine waking up one day and being told that nothing around you is real. Not the sky, not the people you love, not even your own body. Instead, you are simply a brain, floating in a vat of liquid, connected to powerful computers that feed you electrical signals. Every sight, sound, and sensation you've ever experienced is just a simulation, generated to keep you convinced that you are living in a real world. This is the haunting thought experiment known as the brain in a vat. At first, it sounds like science fiction, but the paradox strikes at the heart of philosophy. How do we know that our reality is real? If everything you experience is filtered through your brain, through the signals of sight, touch, taste, and sound, then it is possible that those signals are being fabricated. Your brain cannot tell the difference between electrical impulses from the real world and impulses fed in artificially by a machine. In other words, what if everything you believe about the world is nothing more than an illusion? This idea is not new. The French philosopher René Descartes famously asked how we can know anything at all. He imagined a malicious demon that could deceive our senses, making us believe in a false world. The brain in a vat is the modern version of that demon, updated with computers and technology. If we cannot prove we are not brains in vats, then how can we claim certainty about reality? The paradox doesn't stop at doubt. It forces us to question identity itself. If you are just a brain in a vat, what does that mean about you? Are you still the person you believe yourself to be? If your memories, your personality, and your entire life are programmed illusions, then who is the real you? The paradox suggests that selfhood may be nothing more than information running through circuits, whether in a brain or in a machine. This thought experiment resonates deeply with modern science and culture. In neuroscience, we know that perception is already a kind of simulation. The brain never experiences the world directly. It only interprets electrical signals sent from the senses. What we call reality is already a constructed model. The brain in a vat takes this one step further. If all we ever know is the model, how can we be sure there is a real world beyond it? In popular culture, this idea inspired works like The Matrix, where humanity lives in a computer-generated dream, while their bodies lie motionless in pods. The story captures the essence of the paradox. If the illusion is perfect, how would we ever escape it, or even realize it exists? But some philosophers push back. They argue that even if we were brains in vats, the world we experience still counts as real in a practical sense. After all, our choices still have consequences within that reality, and meaning can still exist even in a simulated world. Reality, they argue, is whatever we consistently experience, whether physical or virtual. Yet, the paradox lingers. It forces us to confront the fragility of certainty. If our senses can be tricked, if our memories can be farfused, then truth itself becomes slippery. The brain in a vat reminds us that knowledge is never absolute. It is always filtered, interpreted, and vulnerable to doubt. At its core, this paradox is not about science fiction, but about trust. Can we trust our own minds? And if not, what does that say about the world we believe we inhabit? Perhaps we are all, in some sense, brains in vats, living inside the constructs of our own minds, never fully certain of what lies beyond. So, the next time you close your eyes and feel the world around you, remember this unsettling question: how do you know it's real? The paradox does not give us the answer. It only deepens the mystery, leaving us floating in unseen, like brains in a vat, dreaming of reality. The Teletransportation Paradox: imagine a future where travel is instant. You step into a machine called a teletransporter, press a button, and in the blink of an eye, you are no longer in your room. You are across the world, standing in another city, ready to continue your day. No airplanes, no trains, no waiting. At first glance, it feels like a miracle of technology, but hidden inside this convenience lies one of the most disturbing questions ever asked about identity and existence. Is the person who arrives on the other side really you? Here's how teletransportation works in the thought experiment. The machine scans your entire body down to the atomic level, recording every particle, every cell, every neuron. Then, it disassembles your body, essentially destroying it, while transmitting the data to a receiving station elsewhere. There, a new body is built, molecule by molecule, perfectly identical to the original, complete with your memories, personality, and even the thoughts you are having at the moment of transmission. To the outside world, nothing has changed. You step in, and you step out, as if you simply teleported. But here's the chilling paradox. Did you die in the process? The original body was destroyed. The new one is just a copy, however perfect. So is the person who walks out of the machine still you, or just a flawless replica who believes they are you? This is the teletransportation paradox, and it cuts deep into our ideas of identity and consciousness. If being you is about having the same memories and personality, then perhaps the copy is truly you. But if being you requires continuity of the same physical body or consciousness, then the process killed you, and what stepped out is someone new, someone who only thinks they are you. Philosophers often push this experiment further. What if the machine malfunctions and does not destroy the original? Suddenly, there are two versions of you, one standing at the departure point, another at the arrival. Both have the same memories, the same identity, the same sense of being you. Which one is the real you? Can both be you at the same time? If not, then which one has the stronger claim to authenticity? The paradox forces us to confront a terrifying possibility. Perhaps identity is not a fixed essence, but a pattern. Just as a song can exist in many recordings, or a flame can exist in many candles, maybe you are simply the arrangement of information that makes up your mind. If that is true, then a perfect copy might be just as real as the original. But if identity is pattern alone, then individuality becomes fragile, easily duplicated, easily replaced. This thought experiment echoes through modern science and technology. In neuroscience, we know that the brain is a network of patterns firing across billions of neurons. If those patterns can be copied, could consciousness be uploaded into a machine? Would the uploaded version truly be you, or just a digital echo? In physics, quantum teleportation already exists on a small scale, not for people, but for particles, raising the unsettling question of whether one day such processes could extend to living beings. The Teletransportation Paradox also speaks to something deeply human, the fear of death. If stepping into the machine destroys the original you, then teletransportation is not travel. It is suicide followed by replacement. Yet, from the outside, no one would ever notice. Your loved ones would greet you as if nothing happened. You would laugh, speak, remember, and believe you survived. But did you? Or did the original vanish forever in that first spark of destruction? This paradox, then, is not about technology. It is about the soul. Is there something unique and indivisible in each of us that cannot be copied? Or are we nothing more than patterns of information that can be rebuilt infinitely? If it is the former, then teletransportation kills us each time we use it. If it is the latter, then death itself may be an illusion, as long as the pattern lives on. In the end, the teletransportation paradox does not give us a clear answer. It leaves us suspended in uncertainty, caught between the fear of loss and the promise of immortality. It asks us, what makes you, you? Is it the body, the continuity, the pattern, or something else entirely? And until we know, stepping into that teletransporter will always feel like stepping into a question you can never escape. The Boltzmann brain paradox. Imagine drifting alone in the vast darkness of space. Around you, galaxies stretch like scattered islands, stars burn and die, and the universe itself expands endlessly. Now imagine that, in this infinite chaos, particles randomly collide and assemble, by pure chance, into a functioning human brain, complete with memories, thoughts, and a sense of self. This bizarre thought experiment is known as the Boltzmann brain paradox. The idea comes from the 19th century physicist Ludwig Boltzmann, who studied entropy, the natural tendency of the universe to move from order to disorder. Boltzmann argued that order, like planets, stars, and life, could emerge from random fluctuations in an otherwise chaotic universe. Over infinite time, even highly improbable arrangements must eventually occur. And so, given eternity, it is not impossible that a brain could randomly form out of scattered particles, floating in the void, with memories of a life it never truly lived. Here is where the paradox begins. If the universe is infinite and eternal, then statistically, it is far more likely for a single brain to spontaneously appear than for an entire ordered universe like ours to form. In other words, the chance of you existing as a random brain, hallucinating your entire reality, may be greater than the chance of you existing in a vast, stable cosmos. That means it is possible, disturbingly possible, that you are not living in a real universe at all. You are just a Boltzmann brain, imagining everything around you. This paradox shakes the foundations of cosmology. Scientists build models of the universe under the assumption that it is real, coherent, and governed by physical laws. But if the Boltzmann brain scenario is true, then the majority of conscious beings in the universe are not the product of stars, planets, and evolution. They are lonely, momentary brains, born out of chaos, vanishing as quickly as they appeared. And if that's the case, how can we trust our understanding of reality? How can we know that our memories, our science, even the feeling of sitting here right now, are anything more than illusions flashing through a phantom brain in the void? The Boltzmann brain paradox also touches on philosophy. It echoes Descartes' radical doubt, what if everything is deception, but takes it further. It is not a demon tricking you, nor a simulation built by machines, but randomness itself, conjuring up the illusion of self. It is solipsism sharpened by probability. If brains like this are more likely than universes like ours, then the rational conclusion would be that you are one of them. Yet this conclusion feels absurd, which is why it is called a paradox. Modern cosmologists use this paradox as a challenge. A good theory of the universe must avoid predicting a reality dominated by Boltzmann brains. If your model suggests that the most common form of consciousness is a random, short-lived brain in chaos, then the theory collapses. The fact that we experience a stable, continuous universe suggests that our cosmos must be structured in such a way that Boltzmann brains are extremely rare or perhaps impossible. On a deeper level, the paradox is about identity and trust. If all your memories could be fabricated in an instant, then what makes you real? If you cannot prove that you are not a Boltzmann brain, then does reality itself lose its grounding? The paradox does not give us a clear answer. It only reminds us how fragile our certainty is. And yet, there is something oddly beautiful in the idea. Even if you were just a Boltzmann brain, born for a flicker of thought before dissolving back into chaos, for that brief moment, you would still experience love, curiosity, and wonder. Reality, whether lasting billions of years or just one fleeting spark, still feels real from the inside. The Boltzmann brain paradox, then, is not just about physics. It is about the haunting fragility of existence. Are we the children of stars, the product of cosmic order, or are we nothing more than brains adrift in eternal darkness, dreaming of a universe that never was? The paradox leaves us with no certain answer, only the unsettling possibility that everything we know may be nothing more than a dream in the mind of chance. The simulation hypothesis paradox. Look around you, the walls, the sky, the people you know, even your own hands. What if none of it is truly real? What if every detail of your life, every sound, every feeling, every memory is not part of a physical universe, but instead part of an advanced computer simulation? This unsettling idea is known as the simulation hypothesis, and it has grown from science fiction into one of the most debated paradoxes of philosophy and science. The paradox begins with a simple question. If future civilizations become advanced enough to run realistic simulations of conscious beings, wouldn't they eventually do it? Imagine a future where computers are powerful enough to simulate entire worlds, complete with people who think, feel, and believe they are real. If such simulations are possible, then logically, there could be millions or billions of them. And if that is the case, then the number of simulated beings would vastly outnumber real biological beings. By pure probability, that means it is more likely that you are one of the simulated beings than one of the originals. This argument was famously put forward by philosopher Nick Bostrom, and it creates a dilemma. Either civilizations never reach the point of running such simulations, or they choose not to. But if they do, then chances are you are not living in base reality. You are a character in a vast experiment, unaware of the code that shapes your world. But here lies the paradox. If we are simulated, can we ever prove it? If everything we experience is generated by the simulation, then all our evidence, our science, our physics, our senses, is part of the program. Even if we discovered glitches, strange patterns, or limits to our reality, how could we tell whether they are signs of simulation or simply the laws of physics? The very tools we would use to uncover the truth are themselves simulated, meaning the truth may forever remain out of reach. This paradox also touches on free will. If we are simulations, are our choices truly ours, or are they determined by the code of the system? Perhaps every decision you make is simply a line of programming playing out, an illusion of autonomy. Or perhaps the simulation allows for randomness, giving you the impression of freedom while still keeping you inside its design. Either way, the question of what it means to be real grows more complex. The simulation hypothesis also echoes ancient philosophy. Plato's allegory of the cave described humans as prisoners mistaking shadows for reality. Descartes wondered if an evil demon might be deceiving us. Today we imagine computer simulations instead of shadows and demons, but the underlying doubt is the same. How can we ever be sure that the world we perceive is the true one? Science, too, wrestles with these questions. Some physicists point to the possibility that our universe has limits, or pixels, the smallest possible units of space and time, similar to the resolution of a computer game. Others suggest that if the laws of physics appear strangely fine-tuned for life, it could be because we are inside a simulation designed for us to exist. Yet none of these ideas can be confirmed without stepping outside the system. And if we are simulated, stepping outside may be impossible. What makes this paradox haunting is not just the possibility that we are simulated, but the implications if we are. If our universe is a simulation, then everything we hold sacred, our history, our struggles, our achievements, could be nothing more than data, erased or rewritten at any moment. The stars we gaze at, the people we love, the lives we build, all could vanish if the simulation shuts down. And yet, even if that were true, would it change anything? If your experiences feel real to you, if your emotions matter, if your choices have meaning within the simulation, then perhaps reality is not defined by its origin, but by its impact. Maybe being simulated does not make life less real, it just makes it mysterious. The simulation hypothesis paradox leaves us with no clear answer. If we are real, then we live in a universe of staggering complexity. If we are simulated, then we are part of a grand design we cannot escape. Either way, the question forces us to confront the limits of knowledge and the fragility of certainty. So the next time you look at the stars, ask yourself, are they burning suns billions of light years away, or patterns of code written to convince you of their existence? The paradox does not reveal the truth, it only deepens the mystery. The paradox of consciousness. Close your eyes for a moment and think about the strange fact that you are aware, not just alive, not just functioning like a machine, but experiencing life from the inside. You don't just process the world, you feel it. You see colors, hear music, taste food, feel pain, and experience joy. This inner world, this private stage of awareness, is what we call consciousness. And yet, here lies one of the deepest mysteries of existence. Why does consciousness exist at all? This is the paradox of consciousness. From a scientific perspective, the brain is a physical system. Neurons fire, chemicals flow, and electrical signals pass through networks. This explains how information is processed, but it doesn't explain why that processing is accompanied by subjective experience. Why does the firing of neurons produce the feeling of red, the sound of a violin, or the ache of sadness? Why is there an inner life at all, instead of a mind that works in silence? This is often called the hard problem of consciousness, a term coined by philosopher David Chalmers. The easy problems of the mind, like how we recognize patterns, store memories, or move our bodies, can be explained in terms of computation and biology. But the hard problem asks, why is there a first-person perspective? Why does matter, when arranged in a certain way, wake up and feel? The paradox deepens when we realize how private consciousness is. You can describe your feelings to others, but no one can ever enter your mind and experience them as you do. Your pain is only yours. Your thoughts, your inner voice, your dreams, they exist entirely within you, unreachable to anyone else. And yet, you have no doubt that others are conscious too. You assume they feel as you feel, even though you can never prove it. Consciousness is both undeniable and unprovable, both intimate and universal. Some scientists argue that consciousness may be an illusion, that our brains only think they have an inner world, when in fact it is just information processing. But if that were true, who or what is experiencing the illusion? If consciousness is not real, then how can we explain the undeniable fact that we are aware right now, in this moment? Others suggest that consciousness might be fundamental, not an accident of matter, but a basic feature of reality itself. This idea, known as panpsychism, proposes that awareness exists in some form everywhere, even in the smallest particles. In this view, consciousness is not created by the brain, but shaped by it, like a radio tuning into signals that are already present. But if this is true, then the universe is alive with awareness, and our individual minds are just tiny sparks in a vast field of consciousness. The paradox also touches on artificial intelligence. If machines can one day replicate the functions of the brain, will they also become conscious? Will they not only process data, but also feel existence? If yes, then consciousness may indeed be just an emergent property of complexity. But if no, then perhaps consciousness requires something deeper than mere computation, something we still do not understand. The mystery of consciousness is not only scientific, but deeply personal. Who are you really? Are you your body, your memories, your brain, or something beyond? And if consciousness is so fragile, tied to the physical state of the brain, what happens to it when the brain dies? Does awareness vanish, or does it continue in some form we cannot yet comprehend? This is why consciousness is paradoxical. It is the most familiar thing. We live it every moment, and yet it is the most mysterious. Science can measure the brain, map its activity, even predict behavior, but no equation can capture the redness of red, the sweetness of chocolate, or the feeling of being alive. Consciousness is both the foundation of our reality and the greatest enigma within it. The paradox of consciousness reminds us of the limits of knowledge. We can explore the stars, split atoms, and decode genomes, but we still cannot fully explain the simple fact of awareness. The mystery is not out there. It is within us, closer than breath, deeper than thought. And perhaps, the paradox suggests, the greatest frontier is not the universe beyond us, but the universe inside our own minds. The genetic bottleneck paradox: every living human on Earth today, all 8 billion of us, carries within our DNA a story older than history itself. Our genes are like a record of survival, passed down through countless generations. But hidden in this record is a startling mystery known as the genetic bottleneck paradox. The discovery that at certain points in our evolutionary past, the entire human species may have been reduced to just a handful of individuals. A genetic bottleneck occurs when a population shrinks so drastically that only a small number of survivors pass on their genes. Imagine millions of people suddenly reduced to only a few thousand, or even a few hundred. In such moments, the diversity of DNA collapses, and entire genetic lineages vanish forever. What's paradoxical is that today's immense variety of humans, from different continents, cultures, and backgrounds, can sometimes be traced back to shockingly small groups of ancestors. For example, genetic studies suggest that modern humans may have gone through severe bottlenecks during times of global catastrophe. One hypothesis points to the eruption of Mount Toba in Indonesia around 74,000 years ago, which may have plunged the Earth into a volcanic winter. According to some theories, humanity's numbers could have dropped to fewer than 10,000 individuals. If true, that means the ancestors of every person alive today were just a small, fragile community clinging to survival against impossible odds. Here is where the paradox takes hold. How is it that such a small genetic base could give rise to the staggering diversity we see today? And how did humanity survive these near extinctions when so many other species perished? The bottleneck suggests fragility, yet the outcome was resilience. Out of scarcity came abundance, out of near destruction came continuity. This paradox is not just about ancient history. Genetic bottlenecks happen in other species too, sometimes creating puzzles for biologists. Cheetahs, for example, are so genetically similar that one cheetah's skin can be grafted onto another with almost no rejection. This lack of variation hints that cheetahs went through a severe bottleneck in the past, reducing their genetic diversity. And yet, despite this weakness, the species survived, though it now faces new dangers from modern extinction pressures. The genetic bottleneck paradox forces us to think about survival in terms of chance and vulnerability. Entire civilizations, entire species may hang by a thread without realizing it. A few lost battles, a single natural disaster, and humanity might never have recovered. The paradox is that despite this fragility, life endures. Against astronomical odds, it pushes forward. There's also a philosophical angle to this paradox. If all humans today descend from such small groups, then in a sense, we are all closer than we realize, distant cousins bound by ancient survival. The divisions we obsess over, race, nation, tribe, are superficial compared to the unity hidden in our DNA. The bottleneck reminds us that our species is not endlessly branching. It has narrowed, squeezed, and restarted many times, yet still found a way forward. And it raises haunting questions about the future. Could humanity face another bottleneck through climate change, war, or cosmic disaster? If we did, who would survive, and what kind of genetic legacy would they leave behind? Would the future of our species once again depend on a fragile remnant, shaping all of humanity to come? The genetic bottleneck paradox, then, is a reminder of both our vulnerability and our resilience. We should not exist, not with so many near misses, not with so many collapses, but we do. We are the children of survivors, carrying in our blood the proof that life can endure, even when it is almost erased. And perhaps the paradox lies in this, that fragility and strength are not opposites, but partners in the great story of survival. The missing link paradox. When we look at the story of human evolution, we imagine a long chain stretching from our ancient ancestors to the people we are today. Fossils and genetic evidence show how life slowly transformed across millions of years, from primitive creatures to apes, and from apes to early hominins, and eventually to modern humans. Yet hidden in this story is a haunting puzzle. The chain is not complete. There are gaps, missing pieces, places where we cannot find the forms that should connect one stage of evolution to another. This mystery is known as the missing link paradox. The term missing link originally referred to the hypothetical creature that bridged the gap between apes and humans. Early scientists believed that somewhere out there was a single fossil showing the exact transition, a half-ape, half-human figure. Over time, discoveries such as Australopithecus afarensis, Lucy, showed us transitional forms, suggesting that evolution is not a leap but a gradual process. Yet, even today, many links remain missing. The fossil record is patchy, with entire stages of development lost to time. Here lies the paradox. Evolution is one of the most well-supported scientific theories, confirmed by genetics, fossils, and biology. And yet, despite this overwhelming evidence, the gaps in the record make it appear incomplete. How can a process so fundamental leave behind a trail so broken? Shouldn't the Earth be overflowing with countless fossils showing each step? Instead, we find scattered fragments, isolated snapshots, leaving us to guess the story in between. The paradox deepens when we realize that the problem may never be fully solved. Fossilization is rare. Most living things decay without leaving any trace. Whole lineages may have risen and fallen without a single fossil surviving to tell their tale. The missing links are not missing because evolution is wrong, but because history itself erased them. Still, their absence creates tension. We know evolution happened, but the details remain shrouded in mystery. Beyond biology, the missing link paradox takes on symbolic meaning. It reminds us that human identity is still uncertain. Are we apes refined by time? Or something more? The missing pieces in our evolutionary story mirror the missing pieces in our understanding of consciousness, culture, and meaning. We search for origins not only in bones, but in the deeper question, what does it mean to be human? This paradox also fuels debates between science and belief. Some critics seize upon the gaps as evidence against evolution, while scientists see them as the natural result of time and chance. Both sides point to the same absence, but draw opposite conclusions. The paradox lies not in the fossils themselves, but in how we interpret them. In another sense, we ourselves may be the missing link. Modern humans carry traces of ancient relatives in our DNA, Neanderthals, Denisovans, and perhaps others yet undiscovered. We are not a separate species sprung from nothing, but a woven tapestry of lineages. The missing links live inside us, hidden in our blood and bones. The missing link paradox challenges us to accept that knowledge is never perfect. The story of evolution is not a complete book, but a collection of torn pages. And yet, even with missing chapters, the message is clear. We are the product of an ancient journey, shaped by time, chance, and survival. Perhaps the paradox is this. We long for certainty, for a neat and unbroken chain. But life is not neat. It is messy, fragile, and full of absences. The missing links remind us that truth can be known even when it is incomplete, and that sometimes what is missing teaches us as much as what is found. The Toxin Paradox. Imagine this strange challenge. A billionaire offers you $1 million today if you can form the genuine intention to drink a toxin tomorrow. The toxin will make you violently ill for a day, but will not kill you or cause lasting harm. Here's the catch. You don't actually have to drink the toxin to get the money. The reward is given the moment you form the intention, and it doesn't depend on whether you follow through. The test is simple. Can you sincerely intend to do something you know you won't actually need to do? This is the puzzle known as the Toxin Paradox, created by philosopher Gregory Kafka. At first, the problem seems easy. Of course, you can just decide to drink the toxin tomorrow, claim the money, and then choose not to go through with it. But the paradox arises when we think more deeply about intention. To form a genuine intention is not the same as making a statement or playing a trick on yourself. Intention means commitment. It means truly resolving to act in a way that would guide your behavior when the time comes. But here's the problem. Once you realize the money does not depend on drinking the toxin, your reason for intending to drink it collapses. You cannot, in good faith, form an intention that you know you will abandon. This paradox forces us to confront the mystery of free will, belief, and rationality. Can we truly choose to intend something we know is irrational? Can the mind trick itself into holding a commitment it has no reason to keep? The Toxin Paradox shows how fragile intention is, caught between reason and desire, logic and motivation. Philosophers use this puzzle to explore the difference between intention and action. We often assume that intentions guide behavior, but in this case, forming the intention is itself the goal. To succeed, you must intend without necessarily acting, but the very knowledge of the setup makes it almost impossible to do so. The paradox reveals a hidden truth. Our minds cannot simply will themselves into belief or intention on command. On a deeper level, the Toxin Paradox mirrors challenges we face in everyday life. Think about New Year's resolutions. You may intend to exercise or quit a bad habit, but if the motivation is not grounded in genuine commitment, the intention collapses when the moment arrives. Or consider promises made to others. You may want to mean them, but without true resolve, they dissolve under pressure. The paradox is not just about toxins and money. It is about the difficulty of aligning thought, intention, and action. It also echoes broader philosophical debates about free will. Are we truly in control of our intentions, or are they shaped by reasons, incentives, sensitives, and unconscious drives? If we cannot simply decide to intend something without reason, then perhaps our freedom is less absolute than we believe. The paradox even stretches into questions of ethics and trust. If someone tells you they intend to do something, can you ever know whether their intention is genuine? Or are all intentions fragile, subject to collapse once incentives change? In the end, the Toxin Paradox does not give us a solution. It leaves us caught in the impossible demand to intend without reason, to commit without necessity. It reveals how strange and delicate the human mind is, and how our inner world of choices and beliefs resists being bent to logic alone. Perhaps the paradox is not about toxins at all, but about the very nature of willpower. We think we control our minds, but sometimes intention slips away the moment we shine a light on it. The paradox of free will. Every day we make choices. You decide what to eat, where to go, whom to speak with, and what words to say. These decisions feel personal, flowing from your own mind and desires. This experience is what we call free will, the belief that we are the authors of our own lives. Yet hidden within this belief is one of philosophy's oldest and deepest riddles, the paradox of free will. The paradox begins with a simple question. If every event in the universe has a cause, then aren't all of your choices determined by what came before? If your thoughts arise from brain activity, and your brain activity is shaped by genetics, environment, and experience, then where is the freedom? If every decision can be traced back to prior causes, then free will seems like an illusion, a story we tell ourselves to make life feel meaningful. But the opposite view is just as troubling. Suppose your actions are not determined. Suppose your choices spring from randomness, disconnected from cause and effect. Then your decisions are not truly yours either. They are accidents, unpredictable sparks with no grounding in reason or intention. In this case, you would not be free, but merely subject to chance. Here lies the paradox. If our actions are determined, we are not free. If they are random, we are not in control. Either way, the idea of free will seems impossible, and yet, we feel free. We live as though our choices matter. We praise and blame people for their actions. We hold ourselves accountable. We plan, we regret, we aspire, all of which only make sense if free will is real. Philosophers and scientists have wrestled with this paradox for centuries. Some propose compatibilism, the idea that free will and determinism can coexist. According to this view, freedom does not mean being free from cause. It means acting according to your own desires and reasoning, even if those desires themselves have causes. Others, known as incompatibilists, argue that true freedom is impossible in a determined universe, and that what we call free will is simply an illusion crafted by the brain. Neuroscience deepens the paradox. Experiments have shown that the brain often begins preparing for an action milliseconds before we consciously decide to act. This suggests that the feeling of choosing may come after the brain has already set the course. Are we simply passengers, narrating choices that our brains have already made? Or is there a deeper layer of consciousness still hidden from science, where true freedom resides? The paradox also raises profound moral questions. If free will does not exist, then how can we hold people responsible for their actions? Are criminals guilty, or are they simply the products of biology and circumstance? Is punishment just, or is it merely society's way of reprogramming individuals? On the other hand, if free will is real, then responsibility carries its full weight, but so does the burden of choice, with all its consequences. Religious and spiritual traditions have long wrestled with this paradox as well. Some view free will as a divine gift, a test of character and morality. Others suggest that destiny is already written, and we merely play out roles assigned to us. Still others see freedom and fate as intertwined. We are free to choose, yet our choices move within the flow of a larger design. In the end, the paradox of free will does not resolve easily. It leaves us standing at the crossroads of reason, caught between determinism and randomness, illusion and truth. Yet, perhaps the paradox itself points to something deeper, that freedom is not absolute but relative, that we are not entirely free but not entirely bound. We are threads woven into a vast tapestry, able to move within patterns we did not choose, yet still shaping the design with every decision we make. So, are you free? The paradox whispers yes and no. You are shaped, you are bound, but within those boundaries you still move, still choose, still carry the weight of your own story. The heat-death paradox: picture the universe not as it is now, full of galaxies, stars, and planets, but as it might be trillions of years from today. A silent, empty expanse where nothing stirs. No light shines, no stars burn, no life moves. The universe has reached maximum entropy, a state of perfect stillness where energy is so evenly spread that nothing new can ever happen. This haunting vision is called the heat-death of the universe, and hidden inside it lies the heat-death paradox. If the universe is heading towards such inevitable lifelessness, how is it that we exist now, in an era of stars and life and energy? According to the laws of thermodynamics, systems naturally move toward disorder, or entropy. Over vast stretches of time, the universe should drift into equilibrium where no energy differences remain to drive processes like life, motion, or even thought. If the universe has existed forever, then it should have already reached this state. So, why do we live in a universe filled with structure, complexity, and vitality instead of one that is already dead? This is the paradox. On one hand, physics predicts a bleak future where all differences in temperature, energy, and motion vanish into uniform silence. On the other hand, we look around today and see extraordinary order, the delicate balance of galaxies, the burning of stars, the very existence of conscious beings capable of asking these questions. If entropy is inevitable, why hasn't it already consumed everything? One possible answer is that the universe is not eternal. It had a beginning. The Big Bang, about 13.8 billion years ago, began with incredibly low entropy, like a tightly wound spring waiting to unravel. Since then, entropy has been increasing, but not yet to its maximum. We exist in a cosmic middle age, between the order of the beginning and the silence of the end. The paradox remains, though. It's why did the universe begin in such an improbably ordered state? Why was the spring wound so tightly in the first place? The heat-death paradox also raises questions about cycles. Some theories suggest that our universe might not end in silence forever. Perhaps, after reaching maximum entropy, it could collapse and restart. Or new universes might bud off from its remains. In such a view, heat-death is not the end, but part of a larger rhythm of cosmic rebirth. Yet, this too deepens the paradox. If universes endlessly rise and fall, why are we living in this particular one, at this rare moment when life is possible? Philosophically, the paradox stirs existential dread. If the ultimate fate of the universe is oblivion, then what meaning can our brief lives hold? Are we just temporary flickers in an inevitable march towards silence? Or Does the very fact that life exists in this short window give it more value, not less? Perhaps our fleeting presence is not a flaw, but the point, a fragile flame burning brightly before the eternal dark. The paradox also reflects back on us as individuals. Just as the universe faces heat death, so too do our bodies move toward entropy. We grow, flourish, and inevitably decline. Yet, within that impermanence lies meaning. The awareness that time is limited gives urgency to our choices, depth to our relationships, and power to our experiences. In this way, the heat-death paradox is not just cosmic but deeply personal. Ultimately, the paradox cannot be solved. It can only be faced. The universe may indeed end in silence, and entropy may erase all patterns of life and memory. But until that time, we live in the rarest of ages, an age of stars, of motion, of thought. The paradox is that against the backdrop of inevitable death, the universe is astonishingly, miraculously alive right now. Olbers Paradox. Step outside on a clear night and look up. The sky is dark, sprinkled with stars. But think about this for a moment. If the universe is infinite, eternal, and filled with stars, then every direction you look should eventually land on the surface of a star. The night sky should be ablaze with light, as bright as the surface of the sun itself. Yet it isn't. Instead, space between the stars is black and silent. This simple observation leads to one of the most puzzling questions in cosmology, Olbers Paradox. First posed clearly in the 19th century by Heinrich Wilhelm Olbers, the paradox asks why the night sky is dark, when, logically, it should be flooded with light. If stars extend forever in every direction, their light should overlap and cover the sky completely, leaving no darkness at all. Imagine walking into a forest so dense that no matter where you look, you only see trees. The night sky, in an infinite universe full of stars, should be the same, completely filled with starlight. So, why isn't it? The paradox led to several possible explanations. Some early thinkers suggested that dust and gas in space might block the light, but this only pushes the problem further. Over time, any matter absorbing starlight would heat up and eventually glow until the sky still became bright. Others argued that maybe our eyes simply couldn't see all the stars, but the paradox is not about perception. It is about physics. If the universe were truly infinite and eternal, the sky should be glowing white-hot. The resolution came with modern cosmology, particularly the discovery that the universe is not static but expanding, and that it had a beginning, the Big Bang. Because the universe has a finite age, about 13.8 billion years, we can only see light from stars within that age. Light from more distant regions hasn't had enough time to reach us yet. The darkness of the night sky is not emptiness. It is a horizon of time. Additionally, as the universe expands, light from distant galaxies is stretched into longer wavelengths, a phenomenon called redshift. Over extreme distances, visible starlight stretches into infrared or microwave radiation, invisible to the human eye. This means much of the missing light is still there, but hidden in wavelengths beyond our vision. In fact, the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang, fills the sky, but only sensitive instruments can detect it. So, Olbers' paradox is not really a flaw in the universe, but a clue to its true nature. The darkness of the night sky is evidence that the cosmos had a beginning, that it is evolving, and that it is far from infinite in time. The blackness above us is not a void, but a window into cosmic history. Philosophically, Olbers' paradox is also profound. The darkness we take for granted every night is not absence but presence. It is the signature of a universe that is young compared to eternity, a universe still unfolding, still alive with change. Without darkness, we would not know that the universe had a birth, nor would we see stars as individual jewels scattered across the night. The paradox teaches us to see the night sky differently. Each patch of darkness is not empty. It is a reminder of the limits of time, of distances so vast light has not yet bridged them. The black sky is proof that we live in a universe that has a story, not an endless static blaze, but a drama of beginnings and endings. In this way, Olbers' paradox transforms darkness into meaning. The reason the night is dark is the same reason we exist. The universe is finite in age, expanding, and evolving. The stars shine out of a darkness that holds the key to everything. The fine-tuning paradox. Look closely at the universe, and you'll notice something strange. It seems almost impossibly balanced for life. The laws of physics, the strength of gravity, the charge of electrons, the expansion rate of the cosmos, all of these numbers fall within an incredibly narrow range. If any of them were slightly different, stars would not form, planets would not exist, and life would never emerge. This astonishing precision is at the heart of the fine-tuning paradox. The paradox begins with probability. Out of all the possible values that the constants of nature could take, only a razor-thin fraction allows for the complexity we see today. If gravity were just a little stronger, the universe would collapse in on itself. If it were weaker, galaxies would never form. If the nuclear forces inside atoms were slightly altered, no stable chemistry would exist. Even the rate of cosmic expansion after the Big Bang had to be tuned within unimaginably tight margins. Too fast, and matter would scatter forever. Too slow, and it would collapse before stars could ignite. And yet, against all odds, we find ourselves in a universe that is not only stable, but bursting with complexity and life. This is the paradox. How can such precision exist in a universe born from chaos? Did the universe know we were coming, or is it just a colossal accident? Is this fine-tuning real evidence of design, or is it an illusion born from our perspective as observers? One explanation is the anthropic principle, which suggests that we can only observe a universe compatible with life, because if it weren't, we would not be here to ask the question. In other words, the universe looks fine-tuned because only in such a universe could observers like us exist. But this answer feels unsatisfying, like saying the lottery must be rigged because someone won, yet ignoring how unlikely it was to win, in the first place. Another explanation is the multiverse theory. Perhaps our universe is just one of countless universes, each with its own laws and constants. In this infinite sea of possibilities, most universes would be barren and lifeless. But by sheer chance, a few would hit the right numbers, producing stars, planets, and eventually life. If this is true, we simply happen to be in one of the rare universes where existence is possible. But the multiverse itself is unprovable. It may remain forever beyond observation, leaving the paradox unsolved. Others argue that fine-tuning might be an illusion. Perhaps the constants of nature could not have been otherwise, that they are necessary, not accidental. Or perhaps new physics, still undiscovered, will reveal deeper laws that make the universe's balance inevitable rather than miraculous. The paradox also raises profound philosophical and spiritual questions. Some see fine-tuning as evidence of intention, a cosmic design woven into the fabric of existence. Others see it as a humbling reminder of chance, that our existence rests on fragile numbers, balanced on the edge of nothingness. Either way, the fine-tuning forces us to confront how improbably rare and precious life is. And there is a deeper personal echo in this paradox. Just as the universe is delicately balanced, so too are our own lives, formed by countless coincidences, chances, and near misses. A different choice, a different accident, and we might not be here at all. The fine-tuning paradox reminds us that existence itself is not guaranteed. It is a fragile gift carved out of impossibility. In the end, the paradox remains unanswered. The universe may be finely tuned by design, by chance, or by necessity, but the mystery itself gives life a strange beauty. Against the infinite chaos of what could have been, we exist, in a universe balanced on the razor's edge, where its stars shine, worlds turn, and consciousness awakens to ask, why? The quantum suicide paradox. Imagine a scientist sitting in a quiet room with a strange machine. The machine contains a gun connected to a quantum device that measures the spin of a particle. If the particle spins one way, the gun fires. If it spins the other, the gun clicks harmlessly. According to quantum mechanics, the spin is completely random, with a 50-50 chance each time. Now, here's the disturbing part. Every time the scientist pulls the trigger, the universe splits. In one branch, the gun fires and the scientist dies. In the other, the gun clicks and the scientist survives. From the scientist's own perspective, they never experience death, because in every branch where they continue to be conscious, the gun never fires. This unsettling thought experiment is called the quantum suicide paradox. The paradox is tied to the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event actually happens, each in its own branching universe. If that is true, then every time a life or death quantum event occurs, there are universes where you die and universes where you survive. From your own viewpoint, you only ever experience survival, no matter how unlikely, because you cannot be conscious in the worlds where you don't exist. Here lies the paradox. If consciousness always follows the surviving branch, then from the scientist perspective, they are immortal. No matter how many times they pull the trigger, they always find themselves alive in one branch of the universe. But this immortality is an illusion. From the outside, other observers see a 50% chance of death each time, and in most universes, the scientist dies quickly. The paradox reveals a clash between subjective experience and objective reality. From within, it feels like survival is guaranteed. From outside, it looks like suicide. This thought, experiment is more than a grim curiosity. It forces us to confront questions about identity, probability, and the nature of existence. If the many worlds interpretation is true, then there are countless versions of you, living out every possible outcome of every decision and random event. But if that's the case, then what does it mean to say you survived? Are you just one thread among infinite others, or do you experience only the branches where you continue to exist? Philosophically, the quantum suicide paradox also raises questions about the meaning of risk. If you always survive from your own perspective, does danger even exist? Or is danger only meaningful when seen through the eyes of others? The paradox highlights how survival, probability, and identity shift when seen through the lens of quantum physics. Critics argue that the paradox is misleading because it assumes consciousness can choose branches in the multiverse. In reality, quantum mechanics does not give us control. It only describes probabilities. Even if many worlds exist, you do not magically jump to the safe one. Rather, countless versions of you exist in parallel, some surviving, some not. To think otherwise may confuse probability with certainty. Still, the paradox lingers in the imagination because it touches on our deepest fears, death, survival, and what it means to experience existence. If true, the quantum suicide paradox suggests that from the first-person perspective, death may never be experienced because consciousness always flows into the surviving branches. But if that is so, then immortality would come at a terrible cost, surviving endlessly in stranger and stranger universes, as those around you vanish in branches where you did not. The quantum suicide paradox is not an encouragement of action, but a philosophical mirror. It shows us how fragile our assumptions about reality are, and how quantum mechanics challenges the boundary between life and death itself. The Doomsday Argument: imagine trying to predict the end of humanity, not by looking at the stars or by studying science, but simply by looking at yourself. That is the unsettling foundation of the Doomsday Argument, a thought experiment that suggests the end of human civilization may be closer than we think. The idea begins with a simple observation. Every human who has ever lived can be assigned a number based on the order of their birth. You are somewhere in the long line of human history. If humanity were to continue for millions of years, producing trillions upon trillions of people, then your birth number would be extremely early in the sequence, like being one of the very first lottery tickets in a game with billions more to come. But if humanity is destined to end sooner, then your birth position suddenly looks far more typical. This is where the argument becomes unsettling. By the principle of mediocrity, the idea that you should assume you are a typical observer, your birth rank gives a clue about how long humanity is likely to last. Statistically, it is more probable that you live somewhere in the middle stretch of human existence, not at the very beginning. That means the total number of humans who will ever live is probably not trillions upon trillions, but closer to hundreds of billions. And if that's the case, then we may be much nearer to the end of humanity than we would like to believe. Here lies the paradox. The Doomsday Argument does not rely on wars, asteroids, or climate change to predict the end. It relies purely on probability and your position in the timeline of human births. And yet, its conclusion feels deeply disturbing, that we might be among the last generations, not the first. Critics argue against this logic, pointing out flaws in its assumptions. Perhaps we are not typical observers at all. Perhaps our position in history tells us not. Hing about the future. Others say the argument misunderstands probability, that just because you are early in the sequence doesn't mean the sequence itself must be short. After all, someone has to be early, even in a very long game. Still, the Doomsday Argument lingers because it forces us to see humanity in a new perspective. It reminds us that civilizations are fragile, species come and go. Extinction is not rare, it is the rule of life on Earth. And unless we take great care, humanity may face the same fate, whether soon or far in the future. The paradox also pushes us toward responsibility. If the future of humanity is not guaranteed, then every choice we make matters. Our survival may depend not only on luck, but on how wisely we act, how we handle technology, climate, and conflict. In this way, the Doomsday Argument is not just a prediction, but a warning. Philosophically, the argument unsettles our sense of place. We like to think of ourselves as the beginning of a vast future, the ancestors of countless generations yet to come. But the Doomsday Argument whispers that we may instead be near the end, standing on the edge of history. In the end, the paradox does not offer certainty, it only offers perspective. Whether humanity lasts 1,000 years or 1,000,000, our time is limited, just as every species' time is. The Doomsday Argument is less about predicting the exact date of the end, and more about awakening us to the fragility of our existence. Perhaps the paradox is not a prophecy, but a challenge. If we fear that the end may be near, then we must act as though the future depends on us, because it does. Humanity may not be eternal, but within the span we are given, we can choose whether to drift toward doom or to fight for survival.